We are discussing ideal conditions in various thermodynamic processes. We have seen constant volume process, constant pressure process. Now let us discuss about constant temperature process. Now let us discuss about constant temperature process. Here there is a piston and cylinder device in which there is gas. So it is an expansion process. It is a constant temperature expansion process. So what is constant temperature process? If temperature is maintained constantly throughout the process, it is constant temperature process. Constant volume means volume remains constant throughout the process. Constant pressure means constant pressure throughout the process, pressure remains constant. So constant temperature through the process, temperature should be constant. Let us consider the expansion process. It is an expansion process. So when gas starts expanding in piston cylinder device, when gas starts expanding, during expansion, generally during expansion, temperature decreases. Generally, whenever gas is expanding, temperature decreases. But actually we want to maintain same temperature throughout the process. So that is what we are interested. We need constant temperature throughout the process. But when the gas is expanding, temperature is decreasing. But we need constant temperature throughout the process. So now what we should do to maintain constant temperature process, what we should do? Actually, during expansion, temperature is decreasing. Let's say the gas initial temperature, there is a gas inside piston cylinder. Suppose initial temperature, let's say T1 is initial temperature of the gas. Suppose initial temperature of the gas is 20 degrees centigrade. So due to expansion, temperature is decreasing. Since the gas is expanding, temperature decreasing. Let's say the temperature decreasing like this. So actually initial temperature 20 degrees centigrade. Due to expansion of the gas, the temperature is falling. Temperature falls to, let's say, 19.99 degrees centigrade. So temperature is falling. Why temperature is falling? Due to expansion of the gas, temperature decreases. So, but we need same temperature throughout the process. We need constant temperature process. Right now, what should be done? To maintain constant temperature process, what should be done? We can do one thing. During expansion, we can supply heat simultaneously. When you supply heat simultaneously, we can maintain same temperature throughout the process. So that's why heat is supplied. So when gas starts expanding, its temperature is decreasing. Again, this temperature should be brought to initial condition. Right now, after expansion is over, it is 19.99 degrees centigrade. Again, it should be brought to 20 degrees centigrade so that it maintains constant temperature process. In order to bring the system from 19.99 degrees centigrade to 20 degrees centigrade, heat should be supplied simultaneously. So isothermal process, constant temperature process, during expansion process, heat should be supplied simultaneously. As the gas is expanding, its temperature is decreasing. In order to maintain same temperature, constant temperature, simultaneously heat is supplied, as we can see from the diagram. So it is expansion process. During expansion process, in order to maintain constant temperature, simultaneously heat is added. So during constant temperature expansion, simultaneously heat should be added. So this is constant temperature expansion process. So by supplying heat simultaneously during expansion process, we can maintain constant temperature. Here we can maintain constant temperature during expansion process by supplying heat simultaneously. So this is constant temperature expansion process. Just now we have seen constant temperature expansion process. Now let us see constant temperature compression process. So there is a piston cylinder device in which there is gas. So this gas maintains constant temperature. Right now this is compression process. So during compression, how the constant temperature process is achieved. Now let us have a look. So there is a gas. During compression, generally temperature increases. Suppose the initial temperature of the gas, let's say 20 degrees centigrade. So when you compress the gas, generally the temperature of the gas increases. During compression, the temperature of the gas increases. Let's say initial temperature T1, 20 degrees centigrade. So due to compression, let's say T2, let's say 20.1 degrees centigrade. Generally, compression process, generally temperature increases. So initial temperature of 20 degrees centigrade. So due to compression, when compression starts, the temperature starts increasing. But right now the process is constant temperature. We need same temperature. That is constant temperature we want. Actually temperature is increasing. So right now this is compression process. So in compression process, how to maintain constant temperature? So right now what can be done in order to maintain same temperature during compression process? So just now we have seen expansion process to maintain constant temperature. So heat added simultaneously, heat is supplied simultaneously so that same temperature is maintained. So right now the temperature of the gas is increasing. So again we need to bring the system temperature 20 degrees centigrade. We need to bring from 20.1 degrees to 20 degrees centigrade. Again we need 20 degrees centigrade, same temperature we want, so that process will be constant temperature. In order to bring the temperature from 20.1 degrees centigrade to 20 degrees centigrade, right now what should be done? Heat should be removed from the gas simultaneously. So during compression, simultaneously heat should be removed. So when you start compressing the gas, temperature is increasing. In order to maintain same temperature, right now heat should be removed simultaneously. In expansion process, heat is supplied simultaneously to maintain constant temperature. But in isothermal compression, in order to maintain same temperature, heat should be removed simultaneously. When heat is removed simultaneously, so the process can be maintained constant temperature. So isothermal expansion process, heat supplied simultaneously. In isothermal compression process, heat should be removed simultaneously so that same temperature can be maintained. So this is isothermal compression process. We are seeing constant temperature process. In constant temperature process, we have seen constant temperature expansion process, and also we have seen constant temperature compression process. Now let us see what is ideal gas equation in isothermal process. Constant temperature process also called isothermal process. Now let us see what is the ideal gas equation. We know ideal gas equation, PV is equal to MRT. This is ideal gas equation. This can also be written as PV by T is equal to MR. So we know very well mass remains constant. In the given container, the mass of the gas remains constant, and we know very well R is also constant. Therefore, M into R is a constant. So this can be written as PV by T is equal to constant. So this can also be written as P1 V1 by T1 is equal to P2 V2 by T2. So right now we are discussing constant temperature process. Right now the temperature remains constant. Just now we have seen in constant temperature process T1, T2 same. Since the process is constant temperature process, that is T1 is equal to T2. Since it's constant temperature process, T1, T2 got cancelled. So right now the equation is P1 V1 is equal to P2 V2. So, P1 V1 is equal to P2 V2. This can also be written as, so this is P1 V1 is equal to P2 V2. This can also be written as PV is equal to constant. So, P1 V1 is equal to P2 V2 means PV is equal to constant. So, this is ideal gas equation in constant temperature process. So, PV is equal to constant. Isothermal process or constant temperature process, the equation is PV is equal to constant. Otherwise, P1 V1 is equal to P2 V2. This is ideal gas equation for constant temperature process. This is something like X5 is equal to constant. PV is equal to constant is something like X5 is equal to constant. From mathematics, X5 is equal to constant is rectangular hyperbola. From mathematics, Xy is equal to constant, it is rectangular, hyperbola. It is rectangular hyperbola. So, this is the ideal gas equation for isothermal process. It is something like Xy is equal to constant. So, Xy is equal to constant, it represents rectangular hyperbola from mathematics. So, this is ideal gas equation for isothermal process. Now, we are discussing constant temperature process. We have seen isothermal compression and isothermal expansion process, and also we have seen ideal gas equation in isothermal process. Now, let us look at pressure volume diagram for constant temperature process. Just now we have seen ideal gas equation for constant temperature process. It is PV is equal to constant. It is something like Xy is equal to constant. So, this is mathematical rectangular hyperbola. So, isothermal process is represented pressure volume diagram. It is like a hyperbola. It is a rectangular hyperbola. Constant volume process, it follows a vertical line. On pressure volume diagram, constant volume process, it follows a vertical line, and constant pressure process, it follows a horizontal line. Now, right now, it is isothermal process. It is rectangular hyperbola. Just now we have seen Xy is equal to constant, it is rectangular hyperbola. So, PV is equal to constant is similar to Xy is equal to constant, and Xy is equal to constant, it is rectangular hyperbola. As we can see from the PV diagram, it is a hyperbola, it is a curve, it is a hyperbola. So, point 1 represents initial condition, initial point. At point 1, the pressure is P1 and volume is V1, and at point 2, the pressure is P2 and volume is V2. So, this 1 to 2 represents constant temperature process, that can also be written as PV is equal to constant. So, this is the PV diagram for constant temperature process or isothermal process. We are discussing constant temperature process. Just now we have seen constant temperature expansion, and also we have seen constant temperature compression, and also we have seen pressure volume diagram for constant temperature process. As we can see from the pressure volume diagram, 1 to 2 represents expansion process. 1 to 2 represents expansion. Here 1 to 2 represents, it is expansion process. During expansion process, pressure decreases, volume increases. As we can see from the PV diagram, during expansion process 1 to 2, pressure decreases, volume increases. Pressure is decreasing, volume is increasing. It is an isothermal expansion, constant temperature expansion. So, during expansion, pressure decreases, volume increases. But right now, this is constant temperature process. Temperature remains constant. It is constant temperature process, temperature remains constant. And just now we have seen in isothermal expansion process, constant temperature expansion process, heat should be supplied to the gas simultaneously. So, 1 to 2 is expansion process, and constant temperature expansion process, heat should be supplied simultaneously. So, during 1 to 2, the gas is expanding, it is expansion process. It is expansion process. Just now we have seen in constant temperature expansion, heat should be supplied simultaneously. So during expansion process, heat should be supplied simultaneously. So this is heat supply. So this is about 1 to 2. Now if you look at 2 to 1, if you look at 2 to 1, pressure is increasing and volume is decreasing. Pressure is increasing and volume is decreasing. So during 2 to 1, pressure is increasing and volume is decreasing, but constant temperature. Process is constant temperature. So during compression, when you compress the gas, during compression process, the pressure increases, thereby volume is decreasing. So as we can see from the diagram, during compression, that is 2 to 1. During 2 to 1, the pressure of the gas is increasing and volume of the gas is decreasing. So during 2 to 1, pressure is increasing and volume is decreasing, but throughout the process, temperature is constant. Constant temperature compression. Temperature is constant. So it is compression process. And we have seen during compression process, heat is rejected. During expansion process, heat is supplied simultaneously. During compression process, heat is rejected simultaneously. So it is compression process. During compression, heat is rejected simultaneously. So 1 to 2, this is 1 to 2 and this is 2 to 1. So 1 to 2, it represents expansion process and heat supplied. So pressure is decreasing, volume is increasing, temperature is constant. And 2 to 1 represents compression process. Pressure is increasing, volume is decreasing, temperature remains constant, and during compression heat is rejected. So this is about isothermal process. Let us see examples of constant temperature process. Examples of constant temperature process. So just now we have seen constant temperature process, that is isothermal process. During expansion process, how the constant temperature is achieved, we have seen. And also during compression process also how the constant temperature process is achieved, we have seen. But this is a hypothetical case. Practically, it does not exist. So constant temperature process we have seen, during expansion we have seen, during compression also we have seen, but in order to maintain constant temperature, practically it is not possible. So right now the question is that why in practical situation it's not possible? Constant temperature, why it is not possible? In case of IC engines, talking about IC engine, it is an IC engine, it is a piston cylinder device. In this situation, it's not possible. Practical situations in IC engines, it is not possible to maintain constant temperature. The reason is that in practical situations, the process is very fast. The IC engine speed is 5000 RPM, 6000 RPM. So the process is very fast. It cannot maintain constant temperature. Just now we have seen how the constant temperature process is achieved. So during expansion process, simultaneously heat we have added to maintain constant temperature, and during compression process simultaneously heat must be rejected. So simultaneously supplying heat to the system and simultaneously rejecting heat from the system. So this is not practically possible, number one. And number two, the process must be extremely slow process. Practical situations, the process is extremely fast. It's very fast process. But in theoretical situation, so this process, whatever we have seen, it is extremely slow process. So that's why, so this is not possible. Isothermal process practically doesn't exist in case of IC engines. So two reasons we have seen. First, simultaneously supplying heat and simultaneously rejecting heat, it is not possible, number one. And number two, process must be extremely slow process. So that's why these reasons restricting the process isothermal not possible in practical situations. So the reasons are why constant temperature is not possible. The reason, number one, simultaneous simultaneously supply and heat rejection not possible. This is number 1. Simultaneously heat supply, heat rejection not possible. Number 2, the process is extremely slow process. Process is very slow process. So because of these two reasons, practically isothermal does not exist in case of IC engines, that is in piston and cylinder devices. So this is number 1 and this is number 2. So in order to achieve isothermal process in practical situations in case of piston and cylinder device in IC engines, so it must be extremely slow process, very slow process. Isothermal process must be extremely slow process in order to maintain constant temperature throughout the process. Throughout the process, to get the same temperature, the process is extremely slow process, and which is not possible in practical situations. So this IC engine cannot be constant temperature, but there are some more examples of constant temperature which can be achieved in practice that we will see right now. We are discussing examples of constant temperature process. So here boiling of water. We are suppose boiling water in the atmosphere. Here, as we can see from the diagram, so there is some liquid water in the container. In the container there is liquid water and atmosphere is exerting pressure. Atmospheric pressure is exerting on the water, as we can see. And here there is a fire and we are measuring temperature during boiling. This is boiling process. During boiling of water, if water is boiling and if you insert a thermometer, it would read 100 degrees centigrade. The temperature during boiling process, it is 100 degrees centigrade. Since the pressure is atmospheric pressure, right now the pressure acting is atmospheric pressure. So pressure is atmospheric pressure. So when you boil the water, in the atmosphere when water is boiling, if you insert a thermometer and if you check the reading, temperature reading, it would read 100 degrees centigrade, and this temperature remains constant. During boiling of water in the atmosphere, the temperature is 100 degrees centigrade, and this temperature will be constant throughout the boiling process. Throughout the boiling process, temperature is constant. This 100 degrees centigrade temperature throughout the boiling process, it is constant. So this is an example of constant temperature process. Throughout the boiling process, here the temperature remains constant. Practically you can check it. You can insert a thermometer during boiling process. At home, you can take a beaker of water and we can supply gas flame. We can supply heat. When boiling started in the beaker, when boiling starts, you can put thermometer and you will get temperature 100 degrees centigrade, because anyway in the room pressure is atmospheric pressure, you will be getting 100 degrees centigrade, and you can observe throughout the boiling process it will be 100 degrees centigrade. So this is an example of constant temperature process. And you may be having a doubt, why the temperature is constant during process? Why the temperature is constant? You will be having a doubt. That we will see temperature is constant. We will see in separate chapter, that is properties of pure. In properties of pure substances, we will be discussing what is phase change process, what is boiling process, and why the temperature is constant during phase change process, boiling process. But right now, this is an example of constant temperature during boiling of water in the atmosphere of constant temperature process. We are discussing examples of constant temperature. Let's consider one more example of human body. Human body maintains constant temperature throughout our life, temperature. And what is human body temperature in degrees centigrade? It is 37 degrees centigrade, temperature of human body. Human body, the temperature is 37 degrees centigrade, that is equal to 98.6 degrees Fahrenheit. So this is human body temperature. In degrees centigrade is 37 and degrees Fahrenheit it is 98.6. So this is our human body temperature, but will it be maintaining constantly or is it changing? So if it maintains constantly, we don't have any problem. We are happy and we are happily working every day. But if the temperature changes, sometimes temperature may change. Generally, the temperature remains constant. Human body temperature 37 degrees centigrade, it is constant. But whenever it changes little bit, suppose increases by 1 degree or 2 degree. If it increases by human body temperature, if it increases by 1 degree or 2 degrees, we say it is fever. So we go to hospital. So if the temperature increases by 1 degree or 2 degrees, we say it is fever. So we are suffering from fever. If it increases by 3 degrees or 4 degrees, if the temperature increases by 3 degrees or 4 degrees centigrade, the body is considered to be very serious. Temperature increases by 3 to 4 degrees, it is very serious condition. If the temperature increases by more than 5 degrees or 6 degrees, it is considered to be dead body. For dead body, the temperature, it increases by 5 degrees or 6 degrees, over. Body is over. So it is considered to be a dead body. So generally, our body maintains 37 degrees centigrade. This is the design of God. God has designed our body in such a way that it is maintaining 37 degrees centigrade constantly. So our body is maintaining constant temperature. In some cases, the temperature is changing, but in our daily life, throughout the day, the body is maintaining constant temperature, that is 37 degrees centigrade. So this is also example of isothermal process. We are discussing ideal gas equations in various thermodynamic processes. Now, let us look at reversible adiabatic process. What is adiabatic process? An adiabatic process is a process in which there is no heat transfer. If there is no heat transfer, the process is called adiabatic process. For adiabatic process, there is no heat transfer. Heat transfer is 0. No heat transfer. So an adiabatic process is a process in which there is no heat transfer. If there is no heat transfer, the process is called adiabatic process. For adiabatic process, we can write P V power gamma is equal to constant. So we can write for adiabatic process PV power gamma is equal to constant, where gamma is adiabatic index, where gamma is adiabatic. So for adiabatic process we can write PV power gamma is equal to constant, where gamma is adiabatic index. Gamma is adiabatic index. So for adiabatic process we can write PV power gamma is equal to constant, where gamma is adiabatic index. And there are different gases. For different gases there are different gamma values. We have different gases. So for monoatomic gas it is 1.67 monoatomic gas. For monoatomic gas, gamma is 1.67. What is monoatomic gas? Monoatomic gas means in gas molecule structure there is single atom. If there is single atom in the gas molecule structure, this is called monoatomic gas. For diatomic gas, gamma is 1.4. Diatomic gas. Diatomic gas. Diatomic gas means there are two atoms in gas molecule structure, that is called diatomic gas. For diatomic gas, gamma is 1.4. For polyatomic gas, it is 1.33. Polyatomic gas. For polyatomic gas, gamma is 1.33. Polyatomic means there are more than two atoms in gas molecule structure. This is called polyatomic gas. So for monoatomic gas, there is single atom in the gas molecule structure. For example, helium gas, argon gas. So these are some examples of monoatomic gas. For diatomic gases, there are two atoms in the structure. For example, oxygen, nitrogen. These are some of the examples of diatomic gases. Polyatomic means there are more than two atoms. For example, CO2 gas, there are CO2, CH4. So these are examples of polyatomic gases. So these are gamma values for different gases. For various gases, this is the gamma value. So monoatomic gas, it is 1.67, diatomic gas, it is 1.4, and polyatomic gas, it is 1.33. So gamma is adiabatic index. An adiabatic process is a process in which there is no heat transfer. If there is no heat transfer, the process is said to be adiabatic process. For adiabatic process, we can write PV power gamma is equal to constant. We are discussing adiabatic process. For adiabatic process, just now we have seen pressure volume relationship, that is PV power gamma is equal to constant. So now let us see pressure volume relationship for adiabatic process. Just now we have seen PV power gamma is equal to constant. PV power gamma is equal to constant. This is pressure volume relationship for adiabatic process. This can also be written as P1 V1 power gamma is equal to P2 V2 power gamma. This can also be rearranged like this. P2 by V1 is equal to V1 by V2. So if you cross multiply again, you will be getting this one, P1 V1 and P2 V2, P2. Let's say this is equation number 1. This is equation number 1. From this equation, Let us write V1 by V2. So, P2 by P1 is equal to V1 by V2 power gamma. So, let us write V1 by V2 from the equation. If you write V1 by V2 from this equation, V1 by V2, V1 by V2 will be equal to P2 by P1 power, it becomes 1 by gamma. This gamma becomes 1 by gamma. So, this is V1 by V2 equal to P2 by P1 power 1 by gamma. Let us say this is equation number 2. Let us say this is equation number 2. So, this is pressure volume relationship. For adiabatic process, this is pressure volume relationship. Same equation, the same equation can be written in the form of 1 and 2. Same equation can be written in the form of equation 1 and equation 2. These are pressure volume relationship for adiabatic process. So, just now we have seen pressure volume relationship for adiabatic process. So, these are pressure volume relationship. Now, let us see temperature volume relationship. Temperature volume relationship for adiabatic process. We have seen ideal gas equation. We have seen ideal gas equation. For ideal gas, PV is equal to MRT. For ideal gas, PV is equal to MRT. This can be written as PV by T is equal to MR. For ideal gas, PV is equal to MRT, PV by T is equal to MR. We know very well mass of gas remains constant. In the given container, the mass of the gas remains constant. Already we have seen previous videos, and R is characteristic gas constant. Already it is constant. So, MR is a constant. PV by T is equal to constant. This can be written as P1 V1 by T1 is equal to P2 V2 by T2. So, PV by T is equal to constant can be written as P1 V1 by T is equal to P2 V2 by T2. This can also be rearranged like this. This can also be rearranged like this. T2 by T1. T2 by T1 is equal to P2 V2 by P1 V1. So, same equation I have rearranged like this. Same equation I have rearranged like this. T2 by T1 is equal to P2 V2 by P1 V1. T2 by T1 is equal to P2 V2 by P1 V1. Let us say this is equation number 3. So, this equation number 2, this is, let us say, equation number 3. Let us say this is equation number 3. So, here in equation number 1, P2 by P1 we have in terms of V1 by V2. So, here also there is P2 by P1. Let us substitute equation 1 in equation number 3. In place of P2 by P1, let us substitute equation number 1. So, substituting equation 1 in equation number 3. Let us substituting equation number 1 in equation number 3. Now, let us substitute here T2 by T1. When you substitute, it becomes T2 by T1 is equal to T2 by T1 is equal to, I am substituting P2 by P1 from equation number 1. From equation 1 I am writing here. So, this equation 1 P2 by P1 I am writing V1 by V2, this becomes V1 by V2, V1 by V2 power gamma. Power gamma, this is P2 by P1, I have substituted here into V2 by V1, into V2 by V1. If you look at this equation, here V1 by V2 term is there and there is V2 by V1. So, let us this also change in the form of V1 by V2. This is V2 by V1. If you write V1 by V2, this if you write V1 by V2, we will be getting power minus 1. You will be getting power minus 1. Same equation I am repeating here. Same equation I am repeating here. So, T2 by T1 is equal to, so this will be same, this expression, this one V1 by V2, it will be same, power gamma into, so this V2 by 1 I am changing the reverse direction, that is V1 by V2. So, this is V1 by V2 I am writing. When you change this one, you will be getting power minus 1. Now, if you look at these two, bases are same. So, when bases are same, we can add powers. Now, let us add powers. So, this becomes T2 by T1 is equal to, bases are same, we can add powers. So, V1 by V2 power gamma minus 1, it is gamma minus 1. Let us say this is equation number 4. Let us say this is equation number 4. So, this is temperature volume relationship. For adiabatic process, this is temperature volume relationship, and for adiabatic process, these are pressure volume relationship, and this equation is temperature volume relationship. And this can also be written as, like this. From this equation, we can write, if you cross multiply T1 V1 and T2 V2, T1 V1 power gamma minus 1, T2 V2 power gamma minus 1, T2 V2 power gamma minus 1. So, T1 V1 and T2 V2, simply this can be written as TV power gamma minus 1 is equal to constant. Simply this can be written as TV power gamma minus 1 is equal to constant. So, for adiabatic process, these are pressure volume relationship, these are temperature volume relationships. Now, we are discussing reversible adiabatic process, and in adiabatic process we have seen pressure volume relationship and this is temperature volume relationship. Now, let us see temperature pressure relationship, temperature and pressure relationship. So, already we have seen these equations. Now, for obtaining temperature pressure relationship in adiabatic process, now let us substitute equation 2 in equation number 4. I am substituting equation 2 in equation number 4. So, here there is V1 by V2, here also there is V1 by V2, substituting equation 2 in equation number 4. Substituting equation number 2 in equation number 4. So, writing equation number 4, this is T2 by T1 is equal to V1 by V2, I am substituting this value, that is P2 by P1, P2 by P1 power. So, this we have replaced with P2 by P1. Here there is gamma minus 1 into 1 by gamma. Here gamma minus 1 into 1 by gamma, this becomes gamma minus 1 by gamma. This becomes gamma minus 1 by gamma. Here there is gamma minus 1 into it is 1 by gamma. This is 1 by gamma. So, this becomes gamma minus 1 by gamma. So, let us write one more step, same equation. Let us write one more time. T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. So, this is temperature pressure relationship. For adiabatic process, this is temperature pressure relationship. So, for adiabatic process, these are pressure volume relationship, and this is temperature volume relationship, and this is temperature pressure relationship. For adiabatic process, there are three types of relations. pressure volume relation, temperature volume relation and temperature pressure relation. These relations are extremely important in the analysis of thermodynamics. We are discussing adiabatic process, and adiabatic process we have seen various types of relations: pressure volume relation, temperature volume relation and temperature pressure relation. So these are ideal gas relations only. For ideal gas, so these are the different various relations. So these relations are for ideal gas only. So for adiabatic process, these are ideal gas relations only. Whatever just now we have seen, pressure volume relation, temperature volume relation and temperature pressure relation, these are ideal gas relations for adiabatic process. Now let us write all equations in the same box. So whatever we have seen just now, we will be seeing the same box, we will be keeping the equations in the same box. So these are ideal gas equations for reversible adiabatic process. Just now we have seen for adiabatic process, pressure volume relationship, temperature volume relationship and temperature pressure relationship. So we are discussing ideal gas relations in adiabatic process. Just now we have seen for adiabatic process, pressure volume relationship, temperature volume relationship and temperature pressure relationship. Now let us see all the equations at a time. So these are ideal gas equations. These are ideal gas equations for reversible adiabatic process. So just now we have seen pressure volume relationship. For adiabatic process, pressure volume relationship is PV power gamma is equal to constant. So this is pressure volume relationship. This can also be written as P1 V1 power gamma is equal to P2 V2 power gamma. This is pressure volume relationship, and we have seen temperature volume relationship like this. PV power gamma minus 1 is equal to constant. This can also be written as T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. And also we have seen temperature pressure relation. So this is equal to P2 by P1 power gamma minus 1 by gamma. So these are the ideal gas relations. These are the ideal gas relations for adiabatic process. So this is pressure volume relation, this is temperature volume relation and this is temperature pressure relations. So these are ideal gas relations for adiabatic process, and these equations are extremely important in thermodynamic analysis. So these relations are extremely important in thermodynamic analysis. Throughout the subject for adiabatic process, we can write three types of relations. There are three types of relations and these are important in thermodynamic analysis. We are discussing adiabatic process. Just now we have seen what is adiabatic process and what are the ideal gas equations in adiabatic process. Now let us look at pressure volume diagram for adiabatic process. So this is pressure volume diagram. So 122 and 221, this process line represents reversible adiabatic process, and the line equation is PV power gamma is equal to constant. Corresponding to point 1, the pressure is P1 and volume is V1, and corresponding to point 2, the pressure is P2 and volume is V2. So this is the pressure volume diagram for reversible adiabatic process. Now let us see in reversible adiabatic process, let us consider expansion process. Reversible adiabatic process, expansion. So we know very well adiabatic process means there is no heat transfer. A process in which there is no heat transfer is adiabatic process. Let us consider there is a piston cylinder device and it is insulated. Piston cylinder device, it is insulated piston cylinder device. Therefore, no heat can enter into the piston cylinder device and no heat can leave. No heat is entering and no heat is leaving. So no heat transfer. There is no heat transfer. As we can see from the diagram, no heat is entering and no heat is leaving. So there is no heat transfer. Now let us consider expansion process. If the gas expands, what happens? Already there is some gas, and here we have not supplied any gas. Here we have not added any heat and we have not removed any heat. We have not added any heat and we have not removed any heat. Already there is some gas inside the piston cylinder device, and if these molecules already they have some energy, in the gas molecules already suppose there is some energy. So with that energy, now the gas is expanding. If the expansion takes place, what happens? Let's say already the temperature of gas inside the piston cylinder device, suppose already in the piston cylinder device, suppose there is a temperature, let's say initially the temperature of gas is 100 degrees centigrade. Inside there is some gas, already suppose it has energy, and the initial temperature, let's say 100 degrees centigrade. So due to expansion of the gas, generally during expansion pressure decreases, thereby temperature also decreases. Generally expansion pressure decreases, temperature also decreases. So since the process is expansion process, temperature falls, because during expansion pressure decreases, thereby temperature also decreases. Let's say after expansion process the temperature is, let's say, 50 degrees centigrade. Initial temperature is 100 degrees centigrade and final temperature is, let's say, 50 degrees centigrade. So what do you understand right now? Here no heat is added and no heat is removed from the gas. Already they have energy, in gas molecules already they have energy, and if the gas is expanding, the energy of the gas decreases. That represents pressure of the gas decreases, temperature also decreases. So what is the conclusion right now is, in adiabatic process, when expansion takes place, the temperature of the gas decreases. In adiabatic process, in expansion process, in adiabatic expansion process, temperature decreases and also pressure decreases. But it is expansion process. During expansion, volume of the gas increases. So just now we have seen expansion process. During expansion, any expansion, pressure decreases. So due to decrease in pressure, temperature also decreases. But during expansion process, volume increases. So in adiabatic expansion process, if the gas expands adiabatically, temperature of the gas decreases. So generally any expansion, pressure decreases, temperature decreases and volume of the gas increases. So this is adiabatic expansion process. So just now we have seen adiabatic expansion process. Now let us consider adiabatic compression. Let's consider adiabatic compression process. So same piston and cylinder device in which there is gas. Now let us compress the gas. If you compress the gas, during compression process, pressure of the gas increases. During compression process, pressure of gas increases. So whenever pressure of the gas increases, temperature also increases. And during compression, volume of the gas decreases. And it is adiabatic process, adiabatic compression. So as we can see from the diagram, adiabatic process means no heat transfer, no heat is entering and no heat is leaving. So there is no heat transfer, but we are compressing adiabatically. Gas is compressed adiabatically. So adiabatic compression process. Generally for any compression when gas is compressed, during compression process, for any compression process, pressure increases. So temperature increases, thereby volume decreasing. Pressure increases, thereby temperature increasing and volume of the gas is decreasing. So what is adiabatic process? No heat transfer. We have not added any heat, we have not removed any heat, just we are compressing gas. When you just compress the gas, its pressure increases, thereby temperature increases. During adiabatic compression process, pressure increases, temperature increases, volume decreases. But in adiabatic expansion process, just now we have seen adiabatic expansion process. During expansion process, pressure decreases temperature also decreases, but due to expansion of the gas, volume of the gas increases. So that is adiabatic expansion process, and this is adiabatic compression process. So this is adiabatic compression. Expansion process. So just now we have seen adiabatic compression process. So during compression, the temperature of the gas is increasing. Let's say initial temperature of the gas T1, let's say 50 degrees centigrade, and final temperature should increase because gas is compressed. During compression, no heat is added, no heat is removed. So when you compress the gas, its temperature should increase. So initial temperature 50 means after compression, temperature should increase. Let's say the final temperature, let's say 100 degrees centigrade. So initial temperature 50 degrees centigrade, after compression temperature is 100 degrees centigrade. So in adiabatic compression process, during compression, the temperature of the gas is increasing. In adiabatic expansion process, temperature of the gas decreases. Now let us discuss polytropic process. We are discussing ideal gas equations in various processes. We have seen constant volume process, constant pressure, constant temperature, and adiabatic process. Now let us discuss polytropic process. Polytropic process. What is polytropic process? Poly means many, tropic means changes. Poly means many, tropic means changes. So polytropic means many changes. Poly means many, tropic means changes. Polytropic means many changes. So what are the many changes? In constant volume process, volume remains constant, and constant pressure process, pressure remains constant. Constant temperature process, temperature remains constant. So every process, some constant is there. But here many changes means here volume changes, pressure changes, temperature also changes. Here in polytropic process, pressure changes, temperature changes, and volume changes. There are many changes. Pressure, volume, and temperature, they change here. So that's why there are many changes here. And just now we have seen adiabatic process. In adiabatic process, there is no heat transfer, but in polytropic process, there is heat transfer. There are pressure, temperature, volume, they change, and also there is heat transfer. So, if you look at adiabatic process and polytropic process, what is the difference? Difference between adiabatic and polytropic. In adiabatic process also, just now we have seen pressure is changing, temperature changing, and volume also changing. And here in polytropic process also, these parameters are changing, but what is the difference? The difference is that in adiabatic process there is no heat transfer, but polytropic process there is heat transfer. There is heat transfer in polytropic process. So that is the only difference. That is the only difference. Here many parameters change. Many parameters change here. That's why this process is polytropic process. So polytropic process is a process in which there are changes, many changes. So pressure changes, temperature changes, volume changes, and also here there is heat transfer. In polytropic process there is heat transfer. And polytropic process, the equation is, for polytropic process, PV power n is equal to constant, where n is polytropic index, where n is polytropic index. So this is equation for polytropic process, where n is polytropic index. N is polytropic index. So a process which follows a relationship PV power n is equal to constant, the process is called polytropic process. So for polytropic process, this is the relationship. And if you look at the adiabatic process equation and polytropic process equation, here the index is changing. For adiabatic process, the index is gamma, and right now for polytropic process, the index is n. So this is the equation for polytropic process, and here there are many changes. That's why the process is polytropic process. So this is about polytropic process. Now, what are ideal gas equations for polytropic process? Just now we have seen what is polytropic process. Now, what are the ideal gas equations? Already in adiabatic process we have seen what are the ideal gas equations. So similar to adiabatic process, polytropic equations also same, but except that index is different. So except the index, everything same. Whatever we have derived in adiabatic process, actually we have derived each and every equation. There is pressure volume relationship, there is temperature volume relationship, and there is pressure and temperature relationship. So whatever we have derived in adiabatic process, everything same except the index. Index is different. So let us write ideal gas equations for polytropic process. So these are similar to adiabatic process. So PV power n is equal to constant. This is pressure volume relationship for polytropic process, where n is index, polytropic index. So this can be written as P1 V1 power n is equal to P2 V2 power n. This is temperature volume relationship. T V power n minus 1 is equal to constant. This is temperature volume relationship. So this can also be written as T1 V1 power n minus 1 is equal to T2 V2 power n minus 1. And also there is temperature pressure relationship. So T2 by T1 is equal to P2 by P1 power n minus 1 by n. This is temperature volume relationship. So these are ideal gas relations for polytropic process. So for polytropic process also there are three types of relations. There is pressure volume relationship, and there is temperature volume relationship, and there is temperature pressure relationship. So these are similar to adiabatic process relations, but except the index is different. Here the index is n. Adiabatic process the index is gamma, and right now the index is n. So these are the ideal gas equations for polytropic process. So just now we have seen what is polytropic process, what is the ideal gas equation in polytropic process, and also we have seen what is n value in various processes. Just now we have seen. So let us see pressure volume diagram in polytropic process. This is the pressure volume diagram. So this 122, 221 line represents pressure volume diagram for polytropic process, and for polytropic process it is PV power n is equal to constant. So corresponding to point 1 the pressure is P1 and volume is V1, and corresponding to point 2 the pressure is P2 and volume is V2. So this is the pressure volume diagram for polytropic process. Now let us discuss in polytropic process expansion of gas in polytropic process. As we can see from the diagram, there is a piston cylinder device in which there is gas. Now heat is supplied to gas in the piston and cylinder device. If heat is supplied to gas, initially when heat is supplied to gas, initially the gas temperature increases. Please concentrate once again. If heat is supplied to gas, initially the gas temperature increases, and simultaneously the gas starts expanding. When heat is supplied to gas, gas starts expanding. Due to expansion, the pressure decreases, thereby temperature also decreases. But initially what is happening? When you supply heat, initially what is happening? When you supply heat, initially the temperature of the gas increases. Due to heat addition, initially the temperature of the gas increases, but simultaneously the gas is expanding. Initially when heat is applied, the temperature increases, simultaneously the gas is expanding. When gas is expanding, the pressure decreases, thereby temperature also decreases. So during polytropic expansion, the pressure decreases, thereby temperature also decreases. So it is expansion process. During expansion, volume of the gas increases. So in polytropic expansion process, during expansion pressure decreases, temperature also decreases, volume increasing. So this is polytropic expansion process. Now let us see polytropic compression process. Now let us discuss polytropic compression process. There is a piston cylinder device. If gas is compressed in polytropic process, if gas is compressed, during compression process, pressure increases, thereby temperature also increases. It is compression process. During compression of gas, pressure increases, thereby temperature also increases. Let us consider initial temperature of gas inside the piston cylinder device. Initially, suppose the temperature of gas, let us say 50 degrees centigrade. Initial temperature T1, let us say 50 degrees centigrade. But due to compression, this is compression process. Due to compression, the pressure is increasing, thereby temperature is also increasing. Let us say compression is over, the temperature T2, let us say 100 degrees centigrade. It is a compression process. During compression, the pressure increases, thereby temperature increases. Initially, suppose the gas temperature inside is 50 degrees centigrade. So due to compression, during compression, the temperature increases, let us say 50 degrees centigrade. After compression is over, right now the compression is over. If compression is over, what is the temperature of gas inside? 100 degrees centigrade. Right now, after compression is over, right now the temperature of gas inside is 100 degrees centigrade. So right now inside 100 degrees centigrade temperature is there, and outside, let us say atmosphere temperature in the atmosphere, let us say 20 degrees centigrade. So inside 100 degrees centigrade, so inside right now 100 degrees centigrade, and outside in the atmosphere 20 degrees centigrade. So we know very well heat flows from high temperature to low temperature. Inside it is 100 degrees centigrade. And outside it is 20 degrees centigrade. Heat flows from high temperature to low temperature. So right now, here heat is flowing from inside to outside. So this is heat loss. This is heat loss, or we can say it is heat rejection. We can say heat loss or heat rejection. Heat rejection. So this is compression process. Please observe carefully. Please observe carefully. So in polytropic compression, temperature is increasing. Initially 50 degrees centigrade. After compression is over. After compression is over, the temperature is 100 degrees centigrade. So after compression is over, inside is 100 degrees centigrade and outside it is 20 degrees centigrade. This is atmospheric temperature. So heat flows from high temperature to low temperature. So it is heat loss. This heat loss is nothing but heat rejection. So heat is rejected. Polytropic compression process, it is rejected. Look at here, this is compression process. During compression, heat is rejected. As you can see from the diagram, during compression, heat is rejected. But in polytropic expansion process, during expansion process, heat is supplied to gas. During expansion, heat is supplied to gas, and during compression process, heat is removed or heat is rejected. So polytropic compression process, heat is rejected, and polytropic expansion process, heat is supplied to gas. So this is about polytropic compression process. So just now we have seen polytropic expansion process and also polytropic compression process. So this is polytropic expansion process and this is polytropic compression process, and this is the pressure volume diagram for polytropic process. So if you look at pressure volume diagram, 1 to 2 is expansion process and 2 to 2 is compression process. 1 to 2 represents 1 to 2 represents it is expansion process. So generally in expansion process, we know very well pressure decreases, thereby temperature also decreases. During expansion process, pressure decreases, temperature also decreases. Just now we have seen polytropic expansion. During expansion of the gas, the pressure is decreasing, thereby temperature is also decreasing. Due to expansion of the gas, the temperature is decreasing. And during expansion, the volume of the gas increases. During expansion, the volume of the gas increases. As we can see from the PV diagram also, during expansion, pressure is decreasing and volume also increasing. So 1 to 2. So pressure is decreasing, temperature decreasing and volume increasing. So during 1 to 2, it is expansion process. Just now we have seen in polytropic expansion process, heat is supplied to the gas. Polytropic expansion process, heat is supplied to the gas. Heat is supplied to gas. It is an expansion process. This is polytropic expansion. 1 to 2 represents 1 to 2 represents it is an expansion process. So pressure is decreasing, temperature is decreasing, volume increasing. So during expansion, heat is supplied. Polytropic expansion process, heat is supplied to gas. Now let us look at 2 to 1. 1 to 2 is over. Now let us look at 2 to 1. During 2 to 1, that is compression. During compression process, just now we have seen in polytropic compression process, during compression, pressure increases, thereby temperature also increases. During compression, pressure increases, thereby temperature also increases. And what about volume? During compression, volume of the gas decreases. During compression process, volume of the gas decreases. Volume decreases. Now let's look at carefully. So right now 2 to 1 is compression process. Just now we have seen in polytropic compression process, during compression process, heat is rejected from the gas. Polytropic expansion, heat supplied to gas, and polytropic compression, heat is rejected. So it is an compression process. So 2 to 1, it is a compression process. During compression, heat is rejected. Just now we have seen in polytropic compression, heat is rejected. So this is heat rejection. It is compression process. So 2 to 1 represents it is compression process. As we can see from the PV diagram, so during compression, that is 2 to 1, pressure of the gas is increasing and volume of the gas is decreasing. Pressure increasing and volume decreasing. So during 2 to 1, pressure increasing, thereby temperature increasing, volume of the gas decreases. So it is a compression process, and in polytropic compression process, heat is rejected. 1 to 2 polytropic expansion, heat is supplied to gas, and polytropic compression, heat is removed from the gas. So this is about polytropic process. Now let us see examples of polytropic process. Polytropic process example. There is a balloon here. Suppose this balloon is heated in the atmosphere. Heating of balloon in the atmosphere, it is an example of polytropic process. Heating of balloon. Heating of balloon. Heating of balloon in the atmosphere. So heating of balloon in the atmosphere, it is an example of constant. It is an example of polytropic process. Here there is a balloon like this. There is a balloon. This is the boundary of the balloon, boundary of the system. Inside there is a gas. Inside there is gas. Balloon is inflated. It is inflated balloon. There is some gas in the balloon. Suppose inside the temperature of the balloon 20 degrees centigrade, and outside in the atmosphere. In the atmosphere, let's say the temperature is 40 degrees centigrade. So inside 20 degrees centigrade, outside 40 degrees centigrade. So due to temperature difference, so heat transfer takes place. There is heat transfer. From atmosphere to balloon, there is heat transfer. There is heat transfer. So outside high temperature is there, inside low temperature is there. So due to temperature difference, there is heat transfer. From outside to inside of balloon, there is heat transfer. So that means this is heating of balloon, heating process. It is heating process. Balloon is absorbing heat. So this is heating process. So heating of this balloon is an example of polytropic, because what is polytropic? Polytropic means there are many changes. Pressure changes, volume changes, temperature changes. There are many changes. Just now we have seen in polytropic process. In polytropic process, pressure changes, volume changes, temperature changes. So since there are many changes, this process, we said it is polytropic process. And right now, this is heat supply process. Balloon is absorbing heat. So heat is added to the balloon. So this process, during this process, there are many changes. So since the gas is absorbing heat, the pressure inside it changes. Inside the balloon, the gas pressure changes. And inside the gas, the temperature also changes. Inside the balloon, the gas temperature changes. And volume also changes. Balloon will expand, because since it is absorbing heat, balloon will expand. Balloon expands like this. Balloon expands like this. So since it is expanding, the balloon is expanding, the volume is changing. So volume is changing. Since it is absorbing heat, inside temperature changes, pressure also changes. There are many changes. During this process, there are many changes. Since there are many changes in this process, this is an example of polytropic process. Heating of balloon in the atmosphere. Heating of balloon in the atmosphere. This is an example of polytropic process. Now let us see n values for various thermodynamic processes. N values for various processes. So just now we have seen for polytropic process, PV power n is equal to constant. So where n is polytropic index, suppose if n value changes, what happens? Let's see if n value changes. Let's say if n is equal to 0, let's substitute n is equal to 0, put n is equal to 0. So V power 0 it is 1. Anything power 0 it is 1. So V power 0 it is 1. So 1 into P, so P is equal to constant. It is P is equal to constant. So if n is 0, the process is constant pressure process. It is constant pressure. Constant pressure process. Let us say n is equal to 1. Let us substitute n is equal to 1. If n is equal to 1, so anything power 1, so V power 1, so x power 1 it is x. Similarly, this V power 1 that is V. So you will be getting PV is equal to constant. If n is equal to 1, PV is equal to constant. PV is equal to constant. So we know very well PV is equal to constant. It is isothermal process. We have seen already for isothermal process PV is equal to constant. So this is isothermal process. Now if n is equal to gamma, let us substitute n is equal to gamma. So this becomes PV power gamma is equal to constant. If n is equal to gamma, this is PV power n is equal, PV power gamma is equal to constant. This is adiabatic process. Just now we have seen it is adiabatic process. Now if n is equal to n, this is PV power n is equal to constant. It is polytropic process. It is already in the form of polytropic process. Let us say if n is equal to infinity, so this process becomes constant volume process. It is constant volume. So just now we have seen ideal gas equations in various processes. For adiabatic process we have seen, and also for polytropic process also we have seen. So for polytropic process we have seen ideal gas equations. Ideal gas equations in polytropic process, just now we have seen like this. There is pressure volume relationship, there is temperature volume relationship, and also there is temperature pressure relationship. So this is temperature pressure relationship for polytropic process. So this is temperature relationship for polytropic. Now this is equal to, so this becomes 1 minus 1 by n. This can be written as n by n is 1 minus 1 by n. So this can also be written as, this power can also be written as 1 minus 1 by n. If you substitute n is equal to infinity, let us substitute n is equal to infinity. 1 minus 1 by infinity. Let us say if n is equal to infinity, we have substituted n is equal to infinity. So 1 by infinity is 0. 1 by infinity is 0, 1 minus 0. This is equal to 1 minus 0, that is nothing but 1. So therefore this is P2 by T1. Left hand side it is T2 by T1. Left hand side it is T2 by T1. So already this equation we have seen in previous videos. This equation already we have seen. What is this equation? T2 by T1 is equal to P2 by P1. What is this equation? Which process equation? It is constant volume process. Constant volume process. So, for each process we have derived what is ideal gas equation. For constant volume process, the equation of ideal gas is T2 by T1 is equal to P2 by P1. If it is constant pressure process, right hand side volumes will appear. For constant volume process, pressures will appear. For constant pressure process, volumes will appear. So, this is equation for constant volume process. So, if n is equal to infinity, what is the process? It represents constant volume process. N equal to infinity, this represents constant volume process. So, n is equal to infinity, it represents constant volume process. So, these are the n values for various processes. So, these are n values for various processes. So, if n is equal to 0, it is constant process. If n is equal to 1, it is isothermal process. If n is equal to gamma, it is adiabatic process. If n is n, that is polytropic process, and if n is equal to infinity, it is constant volume process. These are the n values for various processes, and these are extremely important for examination point of view. In GATE examination and also engineering services examination point of view, these are the important values. N values are important for examination point of view. Now, let us see polytropic index. Let us derive polytropic index. What is the formula for polytropic index? So, we know for polytropic process, P V power n is equal to constant. Now, let us derive what is the equation for polytropic index. For what is the equation for n? Let us apply log on both sides. Applying log on both sides. So, this equation can also be written as P1 V1 power n is equal to P2 V2 power n. So, now let us apply log on both sides. Applying log on both sides. So, just now I have applied log on both sides. So, this is in the form of log AB. Log AB, it is log A plus log B. Log AB is log A, that is ln P1, plus log B, that is ln V1 power n. So, right hand side also it is in the form of log AB, again log A plus log B, that is ln P2 plus ln V2 power n. We know this ln V1 power n can also be written as n ln V1. So, n ln V1 power n can also be written as n ln V1. So, this can also be written as n ln V1. Similarly, this also can be written as n ln V2. So, this is same, this term is same. So, this is n ln V2. So, what we have done is this term we have written like this and this term is written like this. Now, let us separate the terms. So, pressure terms one side and volume terms other side. So, ln P1, so this P2 term can be taken left hand side. If you take this term left hand side, so this is ln P1, this term is same. Let us bring this term left hand side minus ln P2. Right hand side, so n ln V2, let us bring this n ln V1 to right hand side. So, this is n ln V2. So, this term becomes minus n ln V1. Now, this is in the form of log A minus B, log A minus B. So, what is the formula? Log A minus B, log A by B, log A by B, log A by B, log A by B, that is ln P1 by P2. Here n term is common, n is common here, we can take n common. If you take n common, So again, this is also in the form of log A minus log B, log A by B, log A by B, log A by B, that is ln V2 by V1. So now we are looking for n, polytropic index n, we are looking for polytropic index n. So n can also be written like this, therefore n can be written like this, n can be written like this, ln P1 by P2 divided by ln V2 by V1. So this is the equation for polytropic index n. This is the final equation for polytropic index n. So for polytropic process, PV power n is equal to constant. So n can be determined like this. So this is the determination of polytropic index n. So n is equal to ln P1 by P2 divided by ln V2 by V1. So this is polytropic index n. In examination problems, suppose pressures are given, P1, P2s are given, and also V1, V2s are given. If the data is given, pressure volume data is given, we can substitute pressure volume data in this equation, thereby we can calculate what is the polytropic index value. So this is the polytropic index n formula. We have seen ideal gas equations in various thermodynamic processes. For each process, what is the equation? Now let us summarize. We have seen constant volume process, constant pressure process, isothermal process, adiabatic process and polytropic process. Now let us summarize ideal gas equation in each process. Each process, what is ideal gas equation? Now let us summarize. First, let us consider constant volume process. In constant volume process, we have studied like this, T2 by T1 is equal to P2 by P1 when volume remains constant. So this is ideal gas equation for constant volume process. Now let us see what is ideal gas equation for constant pressure process. So for constant pressure process, we have studied like this, T2 by T1 is equal to V2 by V1 when pressure is constant. For constant pressure process, this is the equation. Now let us discuss about constant temperature. What is the ideal gas equation for constant temperature process? For constant temperature process, we have seen PV is equal to constant. So for constant temperature process, ideal gas equation is PV is equal to constant. Now see ideal gas equations in adiabatic process. Let us write ideal gas equations in adiabatic process. In adiabatic process, we have seen equations like this, P V power gamma is equal to constant, T V power gamma minus 1 is equal to constant, T2 by P1 is equal to P2 by P1 power gamma minus 1 by gamma. So in adiabatic process, there are three relations. There is pressure volume relationship, and there is temperature volume relation, and also there is temperature pressure relation. These are ideal gas equations in adiabatic process. And also we have seen for polytropic process, ideal gas equations in polytropic process, similar to adiabatic process equations, but index will be changing. Index is changing, only index is different, and rest of the equations are same. Equations are same, but the index is only difference. Now for polytropic process, what are the ideal gas equations? Now let us see. So these equations are polytropic ideal gas equations are similar to adiabatic process equations, but the only difference is index. Index is different. So we have seen like this, pressure V power P V power n is equal to constant, T V power n minus 1 is equal to constant, T2 by T1 is equal to P2 by P1 power n minus 1 by n. So, these are the ideal gas equations in various thermodynamic processes. Now, let us discuss slope of various processes on pressure volume diagram. Slope of thermodynamic processes on pressure volume diagram. This is pressure volume diagram. So, generally slope is dy by dx. Generally slope is equal to dy by dx. Here x-axis is volume and y-axis is pressure. X-axis volume and y-axis pressure. So, y-axis is pressure. So, this is dP, y-axis is pressure, this is dP divided by x-axis is volume. So, this is dV, this is dV. So, on PV diagram, slope represents dP by d. This is PV diagram, this is pressure volume diagram. On pressure volume diagram, dP by dV represents slope. So, slope is equal to dP by dV. On pressure volume diagram, slope is equal to dP by dV. dP by dV represents slope on pressure volume diagram. Now, let us see what the slope of constant pressure process on pressure volume diagram. So, this is pressure volume diagram for constant pressure process. So, for constant pressure process, P is equal to constant. P constant, it can be written as dP is equal to 0. P is equal to constant means dP is equal to 0. So, just now we have seen dP by dV represents slope. dP by dV represents slope of pressure volume diagram. So, right now dP is equal to 0. If you substitute dP equal to 0, this is 0 by anything, 0 by dV. So, 0 by anything represents 0. So, this is equal to 0. Because dP is 0, 0 by dV. So, 0 by anything it represents 0. So, this is dP by dV. This is slope of pressure volume diagram at constant pressure process. Right now the process is constant pressure. So, this is constant pressure process. So, P represents constant pressure. This is slope of constant pressure line on pressure volume diagram, that is equal to 0. From mathematics, for horizontal line the slope is 0. So, this is pressure volume diagram. For constant pressure it is horizontal line. From mathematics, for constant pressure line it is horizontal line. From mathematics, for horizontal line slope is equal to 0. From mathematics, horizontal line represents slope is 0. So, this is slope of constant pressure process on PV diagram. We are discussing slope on pressure volume diagram. For each process, we are discussing slope of each process on pressure volume diagram. So, now let us consider constant volume process on pressure volume diagram. Already we have seen this is the pressure volume diagram for constant volume process. So, it represents a vertical line. So, at point 1 the pressure is P1, point 2 pressure is P2, but volume remains constant, V1 is equal to V2, we can see from the diagram. So, just now we have seen on pressure diagram dP by dV represents slope. So, slope is equal to dP by dV, just now we have seen slope is equal to dP by dV. On pressure volume diagram, dP by dV represents slope. Now, this is constant volume process. For constant volume process, volume remains constant, V is constant. So, therefore, dV is equal to 0. So, V is equal to constant represents constant volume process. So, V constant means dV is equal to 0. Now, let us write dP by dV let us write dP by dV. So dP by dV represents slope. Right now dV is equal to 0 because constant volume process, dV is equal to 0. So it represents dP by 0. So anything by 0 represents it is infinity. So dV substitute 0. So this is equal to infinity. Anything by 0. So dV 0. So dP by 0 it represents infinity. Anything by 0 it represents infinity. This is slope of constant volume process. This is dP by dV represents slope. Right now the process is constant volume process. Right now the process is constant volume process. So here V represents constant volume process. dP by dV represents slope and V represents constant volume process. So this total term represents slope of constant volume process. Slope of constant volume process on pressure volume diagram, that is equal to infinity. This is slope of constant volume process on pressure volume diagram, it is infinity. So what is the meaning of this? Let us see. It represents infinity. So on pressure volume diagram, constant volume represents it a vertical line. Constant volume line is a vertical line. So for vertical line, mathematically slope is infinity. Constant volume process is vertical line. From mathematics, if you look at vertical line, slope is infinity. So this is slope of constant volume process on pressure volume diagram. Now let us see what is the slope of constant temperature line on pressure volume diagram. This is pressure volume diagram. Right now the process is constant temperature process. So already we have seen for constant temperature process, the equation is PV is equal to constant. You can see from the PV diagram, PV is equal to constant represents constant temperature process. For isothermal process or constant temperature process, PV is equal to constant. PV is equal to constant. So this is the equation for isothermal process. Now let us differentiate this equation on both sides. Differentiating this equation on both sides. Differentiating this equation on both sides. So this is differentiation of PV. So this is in the form of UV formula. This is in the form of UV formula. From mathematics, what is differentiation of UV? U V dash plus V U dash. So let us write UV formula U V dash plus V U dash. So U is equal to P and V is equal to V, U V dash, that is P into dV plus V U dash, that is V U dash is dP. So that is equal to right hand side differentiation of constant. Constant differentiation is 0. This is 0. So this can be rearranged like this. P into dV is equal to minus VdP. This term, if it goes to right hand side, it becomes minus, it is minus VdP. So actually we are looking for slope. So just now we have seen slope is equal to dP by dV. So dP by dV represents slope. So this is dP by dV, dP by dV. So this is equal to P by V and minus sign is there is minus sign. So minus P by V. This is minus P by V. So this is slope of isothermal process. This is slope of isothermal process. Here constant temperature, T represents constant temperature. So dP by dV represents slope of pressure volume diagram and T represents constant temperature. So this whole term represents dP by dV at constant temperature. This represents slope of constant temperature process on pressure volume diagram. Slope of isothermal line on pressure volume diagram, that is equal to minus P by V. This is slope of isothermal process on pressure volume diagram. It is minus P by V. So isothermal slope is negative slope. On pressure volume diagram, the isothermal process slope is negative slope. And what negative sign represents? Now let us see what is the meaning of negative sign. Negative sign represents if one parameter increases, suppose other parameter should decrease. As we can see from the pressure volume diagram, if you look at 1 to 2, pressure is decreasing. if you look at carefully pressure volume diagram, 1 to 2 pressure is decreasing. When pressure is decreasing, what about volume? Volume is increasing. When pressure is decreasing, volume is increasing. So negative slope represents if one parameter decreases. Negative slope represents if pressure decreases, volume increases. Or otherwise, if you look at 2 to 1, during 2 to 1, the pressure is increasing. When the pressure is increasing, volume is decreasing. Pressure is increasing, volume is decreasing. So, negative slope represents pressure increases, volume decreases. So, this is the meaning of negative slope. Negative slope represents if one parameter increases, other parameter should decrease. If pressure decreasing, volume is increasing. Otherwise, if pressure is increasing, volume is decreasing. This is the meaning of negative slope. So, negative slope represents if one is increasing, other will decrease. So, this is slope of isothermal process on pressure volume diagram. It is extremely important. This is extremely important. Slope of isothermal process on pressure volume diagram, it is minus P by V. It is minus P by V. This is slope of isothermal process on pressure volume diagram. It is extremely important. Now, let us see what is the slope of adiabatic process on pressure volume diagram. Adiabatic process. We have studied for adiabatic process, the equation is P V power gamma is equal to constant. P V power gamma is equal to constant. This is for adiabatic process equation. Again, let us differentiate this equation on both sides. Differentiating this equation on both sides. Again, applying UV formula. So, P V power gamma, it is in the form of UV formula, differentiation of UV. So, again writing differentiation of UV, U V dash, that is differentiation of V power gamma. So, differentiation of V power gamma is n into x power n minus 1 into dV. So, this is U V dash, U is P, V dash, that is differentiation of V power gamma. So, differentiation of V power gamma, it is something like n into x power n minus 1 into differentiation of V is dV. So, this is U V dash, this is U V dash plus V U dash. V U dash is V power gamma into dP. U V dash plus V U dash. V U dash is V power gamma into dP. This is V U dash. So, this is equal to differentiation of constant is 0. Differentiation of constant is 0. Now, let us rearrange this one. So, P into gamma. So, this V power gamma minus 1 can be written as V power gamma into V power minus 1 into dV. So, this is equal to, so this goes to right hand side, V power gamma into dP goes to right hand side. This becomes minus V power gamma into dP, minus V power gamma into dP. If you look at this equation, so right hand side there is V power gamma and also left hand side there is V power gamma. So, both sides V power gamma can be cancelled out. V power gamma and V power gamma can be cancelled out. So, now we can write P into gamma, V power minus 1 can also be written as 1 by V. V power minus 1 can be written as 1 by V into dV. So, this is equal to minus dV. So, if you cross multiply, so this V into minus dP. So, right hand side, if you cross multiply P into gamma into dV, so this is equal to minus V into dP. Actually, we are looking for slope. Just now we have seen dP by dV represents slope. We are looking for slope dP by dV. So, this is dP and this is dV. So, dP by dV. So, we need dP by dV. dP by dV, that is equal to, dP by dV is equal to, so this is gamma into minus P by V. If you look at carefully here, so this is dP by dV, dP by dV, dP by dV is equal to here there is minus sign, minus P divided by V into gamma. So, gamma into minus P by V. So, this is slope of adiabatic process. This is slope of adiabatic process. So, left hand side this is slope of adiabatic process, right hand side it is gamma into slope of minus P by V. This is adiabatic slope is equal to gamma into minus P by V, and just now we have seen minus P by V. What is minus P by V? Minus P by V is representing slope of isothermal process. This is slope of isothermal process and this is slope of adiabatic process. So, slope of adiabatic process is equal to gamma into slope of isothermal process. So, this is slope of adiabatic process. This is slope of adiabatic process is equal to gamma into slope of isothermal process. This is slope of isothermal process. So, this is isothermal process slope. So, adiabatic slope is equal to gamma into isothermal slope. So, this is adiabatic slope, slope of adiabatic process on pressure volume diagram. So, that is also equal to, this can also be written as like this. So, adiabatic slope can also be written as, adiabatic slope is equal to gamma into slope of isothermal process. Adiabatic slope is equal to gamma into isothermal slope. So, this is slope of adiabatic process. Now, let us compare constant temperature slope and adiabatic slope on PV diagram. So, comparison of constant temperature slope and adiabatic slope. So, this is PV diagram. Just now we have seen slope of constant temperature process and also we have seen slope of adiabatic process. For adiabatic process, generally we write PV power gamma is equal to constant, where gamma is adiabatic index. Already we have seen gamma is adiabatic index. So, for different gases, what is gamma value we have seen. For monoatomic gas it is 1.67 and polyatomic gas it is 1.33 and diatomic gas it is 1.4. So, 1.33, 1.4 and 1.67. So, these values already we have seen gamma values. So, we can conclude that, so generally gamma is greater than 1. So, why gamma is greater than 1? For different gases, we have seen what is gamma. For monoatomic gas, it is 1.67, diatomic gas, it is 1.4 and polyatomic gas, it is 1.67. So, whatever may be the gas, so gamma is greater than 1. So, just now we have seen gamma is greater than 1. And also we have seen slope of adiabatic process, just now we have seen slope of adiabatic process, dP by dV adiabatic, this is slope of adiabatic process, is equal to gamma into slope of isothermal process. So, this is isothermal slope. So, this is isothermal slope and this is adiabatic slope. So, adiabatic slope is equal to gamma into isothermal slope. Just now we have seen slope of adiabatic process is equal to gamma times isothermal slope, gamma into isothermal slope, and generally gamma is greater than 1. Just now we have seen generally gamma is greater than 1. If gamma is greater than 1, so if gamma is greater than 1, the slope of adiabatic process will be greater than isothermal slope. Gamma is greater than 1. So, therefore, slope of adiabatic process is greater than isothermal slope. So, this is slope of adiabatic process is greater than isothermal slope. So, adiabatic slope is greater than isothermal slope. Why adiabatic slope is greater than isothermal slope? Because gamma is greater than 1. The reason is that gamma is greater than 1. So, that is why slope of adiabatic process is greater than isothermal slope. So, on PV diagram, isothermal and adiabatic, which slope is more? Adiabatic slope is more. So generally slope means dy by dx. So this is constant temperature line and this is adiabatic line. So which line is having more slope? Adiabatic line is having more slope. So that's why isothermal is more or less flat. The slope is less. Slope is dy by dx. It's less. So isothermal is more or less flat, but adiabatic is having more slope, as we can see from the diagram. So isothermal and adiabatic, if we compare, adiabatic line is having more slope. So why adiabatic line is more slope? Because gamma is greater than 1. Since gamma is greater than 1, slope of adiabatic process is greater than isothermal slope. So this is the comparison of isothermal slope and adiabatic slope. Adiabatic is having more slope. We can see from the diagram, adiabatic is having more slope compared to isothermal. Adiabatic is having more slope since the gamma is greater than 1. So this is the comparison of isothermal and adiabatic slopes. Now let us see what is the slope of polytropic process on pressure volume diagram. So this is PV diagram for polytropic process, and for polytropic process the equation is P V power n is equal to constant. This is polytropic process equation. It is similar to adiabatic process, but the index is different. Already we have seen difference between adiabatic and polytropic. The index is different. Just now we have seen the slope of adiabatic process something like this. The slope of adiabatic process dP by dV adiabatic process is equal to gamma times minus P by V. This is slope of adiabatic process. So for polytropic also you will be getting this equation, but the index is different. Only index is different. So for polytropic process, the slope is dP by dV polytropic process is equal to, in place of gamma we will be getting n. So n into minus P by V. So this is the slope of polytropic process on pressure volume diagram. So slope of polytropic process is dP by dV polytropic process is equal to n into minus P by V. So adiabatic slope is negative slope because there is negative sign. There is negative sign. Adiabatic slope is negative slope and polytropic slope also negative slope. And we have seen isothermal slope is also negative slope because isothermal slope is minus P by V. So minus P by V is nothing but negative slope. There is negative sign, there is negative slope. Isothermal slope is negative slope, adiabatic slope is negative slope, and polytropic slope also negative slope. These are negative slopes. And also we have seen what is the significance of negative slope. Negative sign represents slope is negative. Negative slope is nothing but if one is increasing, other is decreasing. So adiabatic slope is negative. Polytropic slope is also negative slope. That means if one parameter is increasing, other parameter is decreasing, as we can see from the pressure volume diagram. So during 1 to 2, pressure is decreasing and volume is increasing, and during 2 to 1, the pressure is increasing and volume is decreasing. So on pressure volume diagram, isothermal slope is negative, adiabatic slope is negative, and polytropic slope is also negative slope. And here this is polytropic slope equation, this is adiabatic slope equation, almost same, but the index is different. Here the index n, polytropic process index is n. So generally for polytropic process, generally for polytropic process, n value is between 1 and gamma. Generally for polytropic process, this is n value between 1 and gamma. So n is greater than 1 and less than gamma. So generally, this is not always. This is not always. Generally in polytropic process, the index n is between 1 and gamma. So it is greater than 1 and less than gamma in general case. But actually it can be minus infinity to plus infinity. In actual practice in polytropic process, it is minus infinity to plus infinity. in actual case, in actual practice, the polytropic index, in actual practice, the polytropic index is minus infinity to plus infinity. That means it can be negative value, it can be positive value, or it can be 0 also. In actual practice, polytropic index can be minus value, it can be plus value, or it can be 0 also. So, it can be minus infinity to plus infinity. This is polytropic index in actual practice. But in thermodynamics point of view, generally means not always, it is not always. In thermodynamics, generally the n value is between 1 and gamma. It is not always, generally between 1 and gamma. So, this is about polytropic index. So, generally in thermodynamics practice, it is between 1 and gamma. In actual situation, it can be minus infinity to plus infinity. N value can be minus value, n value can be 0, or n value can be positive values also. Now, we have seen slope of each and every process on volume diagram. For constant volume process, constant pressure, isothermal, that is constant temperature, adiabatic process and polytropic process. For all the processes, we have seen what is the slope on pressure volume diagram. So, now let us see slopes of all processes on pressure volume diagram. So, when you represent all processes on single PV diagram, this will be the PV diagram for all the processes. This is the pressure volume diagram, slope of all processes in a single pressure volume diagram. And we have already studied what is the n value in different processes. If n is equal to 0, the process is constant pressure. We can see from the pressure volume diagram, if n is equal to 0, the process is constant pressure, and constant pressure process is horizontal line. On pressure volume diagram, constant pressure process is, it is horizontal line. So, as we can see from diagram, so constant pressure n is equal to 0, it is horizontal line, and constant volume process, it is a vertical line. Constant volume process is a vertical line, and n value is infinity. For constant volume process, n is infinity and it is a vertical line, as we can see from the diagram. So, vertical line represents constant volume process and n value is infinity. Horizontal line is constant pressure, n value is 0. And also we have seen, if n is equal to 1, isothermal process. N is equal to 1 isothermal process, as we can see from the pressure volume diagram. So, n is equal to 1, temperature remains constant, and if suppose n is equal to n, it is polytropic process. N is equal to n, it is polytropic process, and n is equal to gamma. N is equal to gamma, it is adiabatic process. You can see from the diagram, n is equal to gamma, it is adiabatic process. N is equal to n, it is polytropic process. N is equal to 1, this is isothermal, and n is equal to 0, it is constant pressure process. And just now we have seen for polytropic process, n value is between 1 and gamma. Generally, for polytropic process, n is between 1 and gamma. Generally, I said, just now we have seen, generally n value is greater than 1 and less than gamma. So, 1 represents, it is isothermal process, n is equal to 1, n is equal to 1, this is isothermal, constant temperature. And n is equal to gamma, n is equal to gamma, this is adiabatic process. And just now we have seen n is between 1 and gamma. So, you can see from the pressure volume diagram. So, this is n polytropic, n is between isothermal and polytropic. Sorry, n is between isothermal and adiabatic. So, if you look at isothermal process, this is isothermal process, this is polytropic process, this is adiabatic process. So, generally n is between 1 and gamma means it represents polytropic process is between isothermal and adiabatic. Polytropic process is between isothermal and adiabatic. You can see from the pressure volume diagram. So, this is polytropic. Polytropic is between isothermal and adiabatic process. Generally between 1 and gamma represents polytropic process is between isothermal and adiabatic process. And generally in expansion process, in expansion process, pressure decreases and volume increases. Generally in expansion, pressure decreases and volume increases. So this side, these lines represent expansion process. So if you look at during expansion, pressure is decreasing. Pressure is these lines, pressure is decreasing, but volume is increasing. Pressure is decreasing and volume is increasing. So these lines represent expansion process. They are expansion. So these line represents expansion process because pressure is decreasing and volume is increasing. These lines are expanding process, expansion process. For compression, process, pressure increases and volume decreases. Generally for compression, pressure increases, volume decreases. So these lines represent compression process because if you look at here, pressure is increasing and volume decreases. Pressure increasing and volume decreasing. So these lines represent compression process. These lines represent compression. So these are expansion lines and these are compression lines. So during expansion, pressure decreases, volume increases. During compression, pressure increases, volume decreases. So this is the total PV diagram for all processes. All processes when you represent on a single PV diagram, so this will be the pressure volume diagram for all the processes. Now let us discuss important terminology in thermodynamics. Thermodynamics terminology. So these terms are extremely important. Let us say system, surroundings, boundary and universe. So these are the important terms. So these terms are extremely important because these terms will appear to system. What is system? What is thermodynamic system? It is not computer system. System means here it is thermodynamic system. What is thermodynamic system? What is thermodynamic system? It is a quantity of matter. It is a quantity of matter on which we are concentrating. It is the quantity of matter which is under study. So the portion we are concentrating or we are analyzing or we are studying, that portion is called thermodynamic system. Here there is some region and here there is some matter, and this matter is concentrated. This matter is being analyzed. So this type of matter which is being analyzed is called thermodynamic system. The matter under study, the quantity of matter. The quantity of matter which is concentrated, which is under study. Quantity of matter concentrated. Or the quantity of matter which is under study. So the quantity of matter which is concentrated or under study, this is called thermodynamic system. It is a quantity of matter concentrated or under study. So this is called thermodynamic system. The portion whatever we are concentrating or we are analyzing, that's called thermodynamic system. Here there are molecules. In this region there are molecules. So these molecules are concentrated. So these molecules are quantity of matter. This matter is concentrated. So the matter which is concentrated or which is under study or which is being analyzed, that's called thermodynamic system. So this is about thermodynamic system. Just now we have seen what is thermodynamic system. So these are the different examples of thermodynamic system. So these are examples of thermodynamic system. Here there is a balloon. In the balloon there is some gas. So this gas in the balloon is thermodynamic system. And here suppose if you concentrate on your mobile phone, so this mobile phone is our thermodynamic system. And here there are two blocks. There is block 1 and there is block 2. Suppose if you concentrate on block 1 becomes our thermodynamic system. Just now we have seen what is thermodynamic system. The portion on which we are concentrating, is our thermodynamic system. It is a quantity of matter on which we are concentrating. Suppose if you concentrate on gas molecules, there is a balloon. In the balloon there are gas molecules. If you concentrate on gas molecules in the balloon, so this gas in the balloon becomes thermodynamic system. If you concentrate on mobile phone, suppose there is a mobile phone on which you are concentrating, so mobile phone becomes our thermodynamic system. And here there are two blocks. Suppose if you concentrate on block 1 is our thermodynamic system. Suppose instead of block 1, if you concentrate on block 2 will be our thermodynamic system. But here block 1 is concentrated. As we can see, there are imaginary line. As we can see, there is imaginary line. So this imaginary line represents on which portion we are concentrating. So the portion on which we are concentrating right now, it is block 1. So block 1 is thermodynamic system. So thermodynamic system is nothing but the portion on which we are concentrating. It is a quantity of matter on which we are concentrating. That's called thermodynamic system. And these are different examples of thermodynamic system. Now what is surroundings? Now let us discuss about surroundings. And generally we say outside the system or external to the system, surroundings. Generally we say outside the system is surroundings, but it is not the complete definition of surroundings. Just now we have seen what is thermodynamic system. So here the quantity of matter which is being analyzed, so these molecules are being analyzed, so we are saying this is thermodynamic system. So generally we say if this is system outside the system or external to the system is surroundings, generally we say, but that is not complete definition of surroundings. Now let us say actual meaning of surroundings. What is the actual definition of surroundings in thermodynamics? So actual definition is the portion outside the system or external to system where the effect is present, that's called surroundings. Here there is system on which we are concentrating. So if this is system outside the system, here some effect is present. If effect is present, then only it is system. Now let us discuss surroundings. What is surroundings? Generally in thermodynamics we say outside the system or external to system, we say surroundings. But this is not actual definition of thermodynamics. Now let us see surroundings. Surroundings. What is surroundings in thermodynamics? Generally we say outside the system or external to system, surroundings, but this is not the complete definition of surroundings. Now let us see actual definition of surroundings. So this is system, just now we have seen the portion on which we are concentrating, so this is system. Outside the system or external to system where the effect is present, if effect is present, the portion outside the system where effect is present, that is only surroundings. So this is the actual definition of surroundings. So the portion outside the system or external to system where effect is present, that's called surroundings. Suppose outside system, if there is no effect, that is not surroundings, that cannot be considered as a surroundings. Suppose this is system, here there is system on which we are concentrating. So outside the system, suppose there is some effect here, in this portion, outside the system, here there is some effect. If some effect is present, some effect is felt here outside the system, so this portion only surroundings, otherwise it is not surrounding. Suppose outside system, effect is not present, it is not surroundings. So this is the actual definition of surroundings. Suppose someone shouting in your room, you are sitting in your room. If someone is shouting in your room, suppose this voice goes outside the room. If this voice is present outside the room, so outside the room can be considered as surroundings. Suppose this voice is not reaching outside the room. Outside the room cannot be considered as surroundings. If someone is shouting outside the room, some effect is felt, some effect is present. So outside the room can be considered as surroundings. Suppose if your friend is there outside and someone is shouting in your room, suppose this outside is not affected. Suppose outside the room, your friend is not able to hear the sound present in the room, that cannot be considered as surroundings. So what is actual meaning of surroundings? So the portion outside the system wherever the effect is present, wherever the effect is felt, that's called surroundings. Now let us discuss boundary. Boundary. What is boundary? It is an imaginary line which separates system and surroundings. Boundary is nothing but it is an imaginary line which separates system and surroundings, that's called boundary. So this is system, the portion on which we are concentrating, that is system. So outside system there is surroundings, just now we have seen outside the system there is surroundings. So there is an imaginary line, we can see from the diagram there is a dotted line. As we can see from the diagram, there is a dotted line. So this dotted line which is separating system and surroundings. So this is an imaginary line which is separating system and surroundings, that's called boundary. So the imaginary line which separates system and surroundings, that's called boundary. Now let us discuss types of boundaries. What are the different types of boundaries? There are different types of boundaries. There is fixed boundary, there is moving boundary, and there is real boundary, and there is imaginary boundary. Types of boundaries: there is a fixed boundary, there is a fixed boundary, there is moving boundary, there is real boundary, and there is imaginary boundary. So these are different types of boundaries. There is fixed boundary, there is moving boundary, there is real boundary, and there is imaginary boundary. There are different types of boundaries. Now let us discuss each one separately. Just now we have seen types of boundaries. Now let us discuss what is moving boundary and what is fixed boundary. There are 4 types of boundaries: moving boundary, fixed boundary, real and imaginary boundaries. Now let us discuss about moving boundary and fixed boundary. So there is a piston cylinder device. This is the piston cylinder device in which there is some gas. Now, right now the piston is at fixed position. Right now the piston is at fixed position. So as we can see from the diagram, there is a boundary. There is a boundary. Here the mass of gas is system. Here there is some mass of gas. So it is the quantity of matter on which we are concentrating. That is our system. So right now the piston is not moving condition. It is at rest condition. So whatever the portion is there, that is system right now. So right now the boundary is not moving. So this is fixed boundary. Right now the boundary is called fixed boundary. If the piston starts moving, when piston starts moving, the boundary also moves. This is called moving boundary, as we can see from the diagram. So right now piston starts moving. When piston starts moving, this is moving boundary. If the piston is not moving, it is at rest condition, that will be fixed boundary. Now we can see this bottom of the system, there is a boundary. This boundary is fixed boundary. As it is not moving, it is fixed boundary. And when the piston starts moving, boundary also moves. This type of boundary is called moving boundary. So this is moving boundary and rest of the boundaries are fixed boundaries. So whenever the boundary moves, it is moving boundary. Whenever the boundary is at rest condition or fixed condition, this is fixed boundary. So this is about fixed boundary and moving boundary. Now let us discuss about real and imaginary boundaries. Let us consider a device. It is a nozzle. Now let us see, this is a nozzle. In the nozzle there is a fluid flow. Whenever the fluid is flowing through the nozzle, here there are 2 surfaces, and right now whatever the surface is there, and it is a real surface. It is a real surface. And what is real boundary? The boundary near to the real surface, that is called real boundary. And here there is no surface, real surface. Here there is no real surface. So the boundary at the imaginary surface, it is a imaginary surface. The boundary at the imaginary surface is called imaginary boundary. Here also there is no surface. So whenever there is no surface, the boundary is imaginary boundary. Whenever there is surface, this boundary is called real boundary. We can see from the diagram, as the fluid is flowing through the nozzle, here there is a boundary. We can see from the diagram there is a boundary. So there are 2 types of boundaries we can see. From this diagram, there are 2 types of boundaries we can see. And here there is a real surface. The boundary at real surface is called real boundary. And we get from the diagram, here there is no surface. There is no real surface. And here there is imaginary boundary. Whenever there is imaginary surface, this boundary is called imaginary boundary. Whenever there is a real surface and boundary near to real surface is called real boundary. So we can see from the diagram. So this is real boundary and this is imaginary boundary. We can see from the diagram there is a real boundary and there is imaginary boundary. Whenever there is a boundary at real surface, this is called real boundary. Whenever there is no surface, if there is no surface, when you take the boundary, this is called imaginary boundary. So these are real and imaginary boundaries. Now let us discuss what is universe in thermodynamics point of view. Universe. Generally, universe, if you see the meaning, so everything if you consider all together, that is universe. But that is not thermodynamic definition of universe. In thermodynamics point of view, universe means system plus surroundings. If you combine system and surroundings, that's called universe. So already we have seen what is system and also we have seen what is surroundings. If system and surroundings are put together, that's called universe in thermodynamics point of view. Here, system means the portion on which we are concentrating, that is system. Outside of system, wherever the effect is present, that's called surroundings, we have seen. If we combine system and surroundings put together, if you combine system and surroundings together, that's called universe in thermodynamics. So in thermodynamics, system plus surroundings called universe. Universe is equal to system and surroundings. System plus surroundings. So what is universe? In thermodynamics point of view, universe is equal to system plus surroundings. If we come system and surroundings, that is universe. Universe is equal to system plus surroundings. So this is the definition of universe in thermodynamics. If we combine system and surroundings, that's called universe. System plus surroundings, that's called universe. Now let us see fundamental definitions in thermodynamics. Fundamental definitions in thermodynamics. So state, what is state in thermodynamics point of view? What is state? What is process? What is path? What is quasi-static process? What is reversible process? What is irreversible process? What is cycle? That is thermodynamic cycle and thermodynamic equilibrium. So these are the fundamental definitions in thermodynamics. So now let us discuss each one separately. Now let us see what is state. State means condition of system. State represents condition of system. Condition of system. So what is condition of system? State means condition of system. Condition means what? Let us see the diagram. So there is a piston and cylinder device in which there is some mass of gas. Mass of gas is 2 kg, pressure is 2 bar and volume is 1 bar. There is mass of gas is 2 kg, as we can see from the diagram. Pressure P1 is 2 bar and volume V1 is 1 meter cube. It is 1 meter cube. So condition of system. Condition means the system is at 2 bar pressure and 1 meter cube volume. This is called condition of system. So system has mass. The system has mass 2 kg and pressure 2 bar and volume 1 meter cube. This is called condition of system. So condition means at what pressure it is. The system is at what pressure and the system is at what volume and system is at what mass. So this is called condition of system and this condition of system is called state. And initial state is denoted by 0.1 and final state is denoted by 0.2. As we can see from the diagram, initial state is denoted by 0.1. 0.1 represents initial state. 0.2 represents final state. But right now this is initial state. Initially the system pressure is 2 bar. So that's why P1 is 2 bar because initial state is denoted by 0.1. So initial pressure P1 2 bar and initial volume V1 1 meter cube. So this is called initial state. State means condition of system. So this is about state. Now let us see the PV diagram. As we can see from the PV diagram, so 0.1 represents initial state. Initial state is denoted by 0.1. Initial state is denoted by 0.1 as we can see from the diagram. So 0.1 represents initial state. So what is initial state? Initial condition. State means condition of system. Initial state means initial condition. So what is initial condition? Corresponding to 0.1 pressure is P1 and volume is V1. So this is initial condition. And what is P1? P1 is 2 bar. And what is V1? V1 1 meter cube. This is initial state or initial condition of system. So this is the pressure volume. This is the piston cylinder device we have taken. So this is the condition of the system and this condition of system is called state. And state can be represented on pressure volume diagram in this manner. So this is about state. So just now we have seen what is state and we have seen initial state is denoted by 0.1. So this is the corresponding PV diagram for state 1. Suppose the gas in the piston cylinder expands. Suppose the gas is expanding. So due to expansion, the condition of system changes. So the condition of system will change and that will be the final state. As we can see from the PV diagram, so this is initial state. Right now it is initial state. Now if the gas is expanding, look at here, if gas is expanding, so this is final state. Due to expansion, the condition of system is changing. As we can see from the PV diagram, what is initial state? Initial state is P1 2 bar, V1 1 meter cube. And right now, due to expansion, the condition of system has been changed. So what is the condition right now? Final condition. Final condition, mass is 2 kg only. P2 1 bar and V2 2 meter cube. The final condition is mass is same, that is 2 kg. So P2, as we can see, P2 is 1 bar and V2 is 2 meter cube. So this is final condition. Just now we have seen state means condition of system. So what is final condition? Final condition is P2 is 1 and V2 is 2 meter cube. This is final condition, and this final condition is called final state. As we can see here, this is final state. So mass remains same, but P2 is 1 bar and V2 is 2 meter cube. As the gas is expanding, it is expansion process. So as the gas is expanding, due to expansion, pressure decreases and volume increases. We know due to expansion, pressure decreases, volume increases. If you look at initial state, what initial state it is P1 2 bar pressure and final state P2 is 1 bar pressure. So initially 2 bar, right now the pressure is 1 bar. That means pressure is decreasing. Why the pressure is decreasing? Because of expansion. Due to expansion, the pressure is decreasing, and due to expansion, volume increases. What is initial volume? Initially V1 is 1 meter cube. Right now what is final volume? V2 is 2 meter cube. Because of expansion, since the gas is expanding, the volume is increasing, so 2 meter cube. So finally the system is at 1 bar pressure and 2 meter cube volume. So this is final condition of system, and this final condition of system is called final state. And just now we have seen initial state is denoted by 0.1 and final state is denoted by 0.2. So P2, V2 is final state. Now we can represent the final state on PV diagram. Let us see the PV diagram. As we can see the PV diagram, so 0.2 represents final state. Corresponding to 0.2, pressure is P2, this 1 bar, and corresponding to 0.2, volume is V2, that is 2 meter cube. So initial state is denoted by 0.1 and final state is denoted by 0.2. So corresponding to 0.2, pressure is P2 and volume is V2. So state is nothing but condition of system, and we can represent the state on PV diagram like this. So this is about state. Now let us discuss about what is process. Process, it means change of state is called process. Change of state. Change of state. So change of state is called process. Change of state. So just now we have seen what is state. State means condition of system. So initial condition is state 1 and final condition is state 2. So this initial condition, there has been some change from initial condition to final, or initial state to final state. There has been some change of state. This change of state is called process. So what is process? Change of state. So expansion is a process. Expansion is a process. Compression is a process. So change of state. During expansion, just now we have seen the change of state is taking place. The system state is changing. So this change of state is called process. Now let us see the diagram. So just now we have seen this diagram. So that is initial state and this is final state. Due to expansion, the state has been changed. System state has been changed to final state. So this change of state is called process. Initially state 1, so P1 2 bar and V1 1 meter cube, and final state is P2 1 bar and V2 2 meter cube. So this state has been changed. Initial state is different and final state is different. This change of state is called process. Change of state is called process. This change of state is process. So initial state, just now we have seen, denoted by 0.1. At 0.1, P1 2 bar and V1 1 meter cube, and final state is denoted by 0.2, and at 0.2 corresponding to final state, P2 is 1 bar and V2 is, so just now we have discussed. So 0.1, this is the condition, 0.2, this is the condition. So initial state, final state, the condition, initial condition, final condition, is it same or different? It is different. Initial condition is different, 2 bar 1 meter cube, P1 V1 different, final condition is different. So now the state has been changed, the condition of the system has been changed. So this change of state is called process. This change of state, change of state is called process. So this process we can represent on PV diagram. Let us see the PV diagram. So this is the PV diagram. So 0.1 represents state 1, 0.2 represents state 2. So this 1 to 2, from 1 to 2 we can see from the PV diagram, from 1 to 2 there is a change of state. This change of state is process, and this 1 to 2 represents process. On PV diagram, 1 to 2, this 1 to 2 represents process. 0.1 represents state 1 and 0.2 represents state 2. This 1 to 2, as we can see from the PV diagram, this 1 to 2 represents, it is a process. So corresponding to 0.1, pressure is P1 and volume is V1. Corresponding to 0.2, pressure is P2 and volume is V2. This 1 to 2 represents it process. So this is about process, and this is the PV diagram for a process. Now let us discuss what is path. Path. Path means it is a line which is connecting various state points. The line which joins or which connects various points is called path. It's a line which connects various points. Various state points. So this is called path, the line which connects various state points. Just now we have seen state points means state 1 means initial state, state 2 means final state. So the line which is connecting various state points, this is called path. This is called path. Now let us see the PV diagram. As we can see from the PV diagram, so just now we have seen this one. So state 1, 0.1 represents state 1 and 0.2 represents state 2. So 1 to 2 there is a line. The line which is connecting state 1 and state 2, this line is called path. The line which is joining state 1 and state 2, this line which connects different state points, this line is called path. So this 1 to 2 there is a line, the line which is connecting 0.1 and 0.2, this line is called path. So path means It is a line which connects various state points. This is called path. Now, what is quasi-static process? Quasi-static process. Quasi means almost, static means rest. Quasi means almost. Quasi means almost, static means rest. Static means rest. So, quasi means almost, static means rest. So, quasi-static means almost to rest. Almost to rest means it is an extremely slow process. Quasi-static process is a process. It is extremely slow process because almost to rest, extremely slow process. It is extremely slow process. So, if a process is extremely slow process, this process is called quasi-static process. Now, let us look at the diagram. So, there is a gas in the piston and cylinder device. So, this gas starts expanding. This gas starts expanding extremely slowly. If the gas starts expanding extremely slowly, this process is called quasi-static process. So, it is an extremely slow process. So, the gas is starting expanding. Gas starts expanding extremely slowly, As we can see from the diagram, it is extremely slowly moving. The gas is expanding extremely slowly. So, this extremely slow process is called quasi-static process. And let us see the pressure volume diagram, PV diagram for quasi-static process. So, here we can see pressure volume diagram for quasi-static process. So, each point is equilibrium point. As we can see from the diagram, there are so many points. Each point is equilibrium point. Equilibrium point or rest. Rest means equilibrium. Static means rest, or it is also called equilibrium. So, each point is equilibrium. Each point is equilibrium point. So, static means rest or equilibrium. Static means rest or equilibrium. Equilibrium means rest, or rest means equilibrium. So, it is expanding. The gas is expanding extremely slowly. When it is expanding extremely slowly, each point represents equilibrium point, because each point represents the system is in rest condition. So, each point represents equilibrium point. So, there are so many equilibrium points. So, this is the extremely slow process. So, this extremely slow process is called quasi-static process. So, what is quasi-static process? It is an extremely slow process in which each point represents equilibrium point. Each point is equilibrium point, rest point. So, this process is called quasi-static process. So, just now we have seen what is quasi-static process, and also we have seen PV diagram for quasi-static process. So, this is the PV diagram for quasi-static process. So, each point is equilibrium point. Just now we have seen. So, there are equilibrium points. So, it is an extremely slow process. So, the pressure changes during this process, pressure changes, volume also changes, but the changes are negligible. So, as the gas is expanding, the pressure changes, pressure decreases because it is an expansion process. We have considered expansion process. During expansion, pressure decreases, we know, but the process is extremely slow. The pressure changes, but the change in pressure is negligible between 2 points, as we can see from the diagram. So between any 2 points, the pressure changes. The pressure changes, but the change in pressure is negligible. Let's say the pressure change dP is equal to 0.001, let's say. So there is a pressure change, there is a pressure drop because it is expansion. Since it is an extremely slow process, the change in pressure is negligible. So it is a negligible pressure change. 0.00 something means it is negligible. So we can say, so pressure change is almost equal to 0. It is not equal to 0. Please understand carefully. This is not equal to 0. Since it is 0.00 something, so we say it is negligible. There is pressure change, but it is negligible. Similarly, as we can see from the PV diagram, so during expansion, the volume also changing. The volume also changes, but it is negligible. There is change in volume. As it is expanding, there is change in volume, but this change in volume is not significant. Let's say the change in volume is equal to 0.01. Let's say 0.01 meter cube. So 0.01 meter cube, there is change in volume, but this is negligible. So we can say the change in volume is almost negligible, almost to 0. So a quasi-static process is a process. It is an extremely slow process, and each point is equilibrium point, and the pressure change in pressure is 0, almost to 0. The change in pressure is almost to 0. The change in volume is almost to 0. So this is the characteristics of quasi-static process. The property changes are negligible. Change in pressure is negligible. Change in volume is negligible. So this is about quasi-static process. Now, what is reversible process? Reversible process. As the name implies, reversible means when you reverse the process. When a process is reversed, if it follows the same path, the process is said to be reversible. A process, when it is reversed, a process when it is reversed, process when reversed, a process when it is reversed, if it follows the same path, if it follows the same path, this process is reversible process. So reversible process, when a process is reversed, if it follows the same path, this process is reversible process. When the process is reversed, follows the same path, if it follows the same path, the process is reversible process. So this is the definition of reversible process. So just now we have seen what is the definition of reversible process. So what definition says is that when you reverse the process, it should follow the same path, then it is reversible. Look at this piston and cylinder device in which there is gas. So, as we can see from the diagram, during 1 to 2 it is expansion process. So, initially when gas expands from 1 to 2, look at the diagram 1 to 2. So, 1 to 2 represents expansion process, 1 to 2, it represents expansion process. And 2 to 1 it represents compression process, 2 to 1 it represents compression. So, during expansion and also during compression, if it follows the same path, this process is said to be reversible process. So, the initially gas is expanding from 1 to 2, during expansion it is 1 to 2, and during 2 to 1 it is compression process. So, 1 to 2 expansion, 2 to 1 compression. Now, let us see the PV diagram. PV diagram, if you look at PV diagram, so this is PV diagram. So, as we can see from the PV diagram, 1 to 2 represents expansion process, because during expansion process pressure decreases, during expansion pressure decreases and volume increases, as we can see. So, during 1 to 2, that is expansion, pressure is decreasing and volume is increasing, and during 2 to 1 compression process pressure is increasing and volume is decreasing. So, during compression process pressure is increasing and volume is decreasing. So, during 1 to 2 and 2 to 1, as we can see from the PV diagram, it follows the same path, 1 to 2 expansion. After expansion is over, during 2 to 1 also it follows the same path, it is following the same path. Since it is following the same path, when you have reversed the process, so since it is following the same path, so this process is said to be reversible. So, why it is reversible process? After you have reversed the process, it is following the same path. Since it is following the same path, this process is reversible process. So, 1 to 2 expansion process and 2 to 1 compression process. So, during both 1 to 2 and 2 to 1 exactly it follows the same path. Since it follows the same path, when you have reversed, so this process is reversible process. So, a reversible process is a process when you have reversed, it follows the same path, this process is reversible process. Now, what are the conditions for reversibility of a process? Just now we have seen definition of reversible process. So, under what conditions a process is reversible? Now, let us see conditions for a reversible process. For a reversible process, the process has to be extremely slow process. For a reversible process, the process has to be extremely slow. So, the process has to be extremely slow process. So, which process is extremely slow process? Already we have seen when a process is extremely slow, or if the process is extremely slow, what is this process? Yes, it is quasi-static process. So, the process extremely slow means it is quasi-static process. It is quasi-static process. So, number 1, the condition number 1, the process has to be extremely slow, that is quasi-static process. And the point number 2, there should not be any friction, no friction between components. There should not be any friction. Friction should not be there. No friction. Friction should not be present. So during this process, there should not be any friction. Friction should not present. And number 3, condition number 3, there should not be any effect on system and also surroundings. No effect on system and surroundings. There should not be any effect on the system and also surroundings. So these are the 3 conditions. If these 3 conditions are satisfied, then only we can say a process is reversible process. So now let us discuss each one in detail. So the process is extremely slow process. So just now we have seen, as we can see from the PV diagram, if the process is extremely slow, so each point is equilibrium point. There are so many points. So these points are equilibrium points. So when we will be obtaining these points, equilibrium points, already we have seen in quasi-static process, when the process is extremely slow process, so these points are obtained. So since the process is extremely slow, each point is equilibrium point. This we have already seen. So the process has to be extremely slow, number 1. And there should not be any friction. During piston cylinder motion, there should not be any friction between piston and cylinder. During friction, due to friction, some energy loss will be there. Due to friction, some energy loss will be there. There will be some energy loss. There is friction. If there is friction, some energy loss will be there. So there should not be any friction. So 122 and 221 exactly the path should be same. So in order to maintain 122 and 221, the path is exactly same. The process should be extremely slow. Then only when you reverse the process, it follows the same path. If the process is extremely slow, then only 122 and 222, 221 exactly it will follow the same path. That is, process must be quasi-static, and there should not be any friction. If there is friction, some energy loss will be there. So there should not be any effect on system and surroundings. There should not be any effect on system and surroundings. What is this point? Now let us see. Suppose there is a piston and cylinder like this. So this is system and this is surroundings. And just now, point number 2, friction should not be there. Generally, when piston reciprocates, there will be some friction. As the piston reciprocates, there will be some friction. So there should not be any friction. Due to friction, some energy loss will be there. So no effect should be present on the system as well as surroundings. Suppose heat is added to system. Suppose 100 kilojoule heat is added to the system. Since heat is added to the system is expanding, thereby it is producing work output, let us say 100 kilojoule. So 100 kilojoule supplied to system in the form of heat. So system is delivering 100 kilojoule work. Since Q is completely equal to W, because of no friction. When there is friction, there will be some energy loss. The complete 100 cannot be converted into 100 kilojoule work. Since friction is neglected, friction is not present, so this 100 kilojoule converted directly into 100 kilojoule work. So let's say this is 1 to 2, this is 1 to 2. So during 1 to 2, it is expansion process, heat is added, work is obtained, it is 1 to 2 process. Now 2 to 1, 2 to 1, let's say work is supplied 100 kilojoule, work is supplied 100 kilojoule to the system. So therefore the system is losing, this is heat supply and this is heat rejecting. So system is rejecting 100 kilojoule. So when heat is supplied to the system, system is producing work and 100 kilojoule supplied, 100 kilojoule work is produced. Since there is no friction, so no friction, no energy loss, directly 100 kilojoule heat is converted to 100 kilojoule work. Now if work is supplied, 100 kilojoule work is supplied to the system and system is rejecting 100 kilojoule. So right now what is effect on system? There is no effect on system because 100 kilojoule supplied, 100 kilojoule rejected. And what is effect on surroundings? 100 kilojoule work is done on the surroundings and surroundings are supplying same 100 kilojoule. So right now no effect on surroundings and no effect on system. So this is reversible process condition. So no effect should be present on the system and surroundings. Right now no effect on the system, no effect on the surroundings. So this is condition number 3. So these are the conditions for reversible process. So there should be extremely slow process, that is process has to be quasi-static process and there should not be any friction between piston cylinder and no effect should be there on the system as well as surroundings. So these are the conditions for reversibility of a process. Now let us see representation of reversible process on PV diagram. So representation of reversible process. So just now we have seen what is reversible process and what are the conditions for reversible process. Now PV diagram for reversible process. As we can see from the PV diagram, so there is a continuous line, a solid line, we can see there is a solid line. This is a solid line, it represents reversible process. Now let's see how this solid line is obtained. Already we have seen what is reversible process. So reversible process means 1 to 2 and 2 to 1 exactly the same. During 1 to 2 and 2 to 1 exactly, if it follows, it is a reversible process. Already this we have seen. So each point is equilibrium, it is extremely slow process, there should not be any friction. So each point we have seen equilibrium condition. So when you join each and every point, there is a continuous line or solid line. There is a continuous line. There is a continuous line. Continuous line or solid line. Since each point is equilibrium, we can join each and every point. We can join each and every point. By joining each and every point, we are obtaining continuous line. We are obtaining, by joining each and every point, we are obtaining continuous line or solid line. As we can see here, there is a continuous line, there is a solid line. Throughout the syllabus of thermodynamics, whenever there is a solid line or continuous line, this line stands for reversible process. Continuous line or solid line, it represents the process is reversible process. Since the process is extremely slow, each point is equilibrium. By joining each and every point, there is a continuous line, there is a solid line. So this is the representation of reversible process. So just now we have seen representation of reversible process on PV diagram. So there is a continuous line, there is a solid line. just now we have seen pressure volume diagram like this. There is a pressure volume PV diagram. So there is a continuous line. Let's say this is point number 1, this is point number 2. So since the process is extremely slow and the friction is negligible, so that's why 1 to 2 and 2 to 1 exactly it follows the same path. So that's why this process is reversible. Since 1 to 2 and 2 to 1 exactly it follows, so we are obtaining a continuous line. So continuous line stands for reversible process. Just now we have seen continuous line stands for reversible process. So in our subject analysis, integration is possible only for reversible process. Integration is possible only for reversible process. Possible for reversible process. Integration. What is integration? Integration. What is integration? Integration means summation. Since each point is equilibrium, we are adding each and every point. Integration means summation. So from 1 to 2, there are so many equilibrium points. These points we are joining. These points we are adding. So that's called integration. So since the process is extremely slow, each point is equilibrium, we can join each and every point. By joining each and every point, we are getting this type of line, continuous line or solid line. So integration is possible only for reversible process. Integration is possible only for reversible process. So throughout the process, it is an extremely important point. Throughout the subject, whenever we are integrating something, integration. Whenever we are integrating something, remember the process must to be reversible process. So integration is possible only for reversible process. Number 1. And area has to be applied only for reversible process. Area. So we can project this area. Area has meaning only for reversible process. So what is area? So there is a process like this on PV diagram. We can project like this. We can project the points like this. By projecting the points like this, we can find the area. So this is area under the curve. So this is area for this 1 to 2 process. For this 1 to 2 process, this is representing area. And you remember, this area is valid only for reversible process. Area has meaning only for reversible process. It is an extremely important point throughout the subject. Area has meaning in only reversible process. Since it is a continuous line, it is a solid line, we can project the area. Like this. So since we are projecting this area, and this is a reversible process. For a reversible process only we can project area. So area has meaning in only reversible process, and integration is possible only for reversible process. So these 2 points are extremely important. Integration is valid only for reversible process, and area is possible only for reversible process. Just now we have seen what is reversible process. But why we need to study reversible process? Why we need reversible process? Why we need reversible process? Actually, reversible process is a hypothetical process. It is imaginary process. It is idealized process. Reversible process is hypothetical. It is a hypothetical process. It is hypothetical process. It is a hypothetical process. It is imaginary process. It does not exist in practice. In practical situations, this process does not exist. Next, immediately there will be a question. If practically it does not exist, why we need this process? In the analysis of the thermodynamic subject, why we need this process? That is the question right now. So, why we are discussing reversible process? The reason is that it is easy to analyze, it is easy to understand. It is easy to understand. It is easy to understand or easy to analyze. Easy to analyze. So, these are the reasons that we are discussing why we are discussing a reversible process. So, these are the reasons why we are discussing a reversible process. So, why we are discussing a reversible process means it is a reversible process and it is easy to understand, easy to analyze. In practical situations, the process is extremely fast. Just now we have seen reversible process means it is extremely slow process. So, practical situations, the process will be extremely fast. So, those processes actually we can't analyze. Practical situations we can't analyze. The process is very fast, we can't analyze those processes. So, if you take IC engine, practically it is very fast, it is at 5000 RPM, 6000 RPM, extremely fast. So, the speed of the IC engine, that is internal combustion engine, that is two-wheelers and four-wheelers, we are using bikes and four-wheelers. So, IC engine speed is extremely fast, the speed is 5000 RPM, 6000 RPM. So, the speed is very fast, we can't analyze those processes. So, to analyze what is happening in IC engine, what is happening in our power plants, we take a hypothetical process and which is extremely slow process. This process, this hypothetical process or idealized process, idealized process, idealized process. So, this hypothetical process or this idealized process, this process is a reversible process. So, why we are using reversible process in our analysis? Because it is easy to understand. Since the process is extremely slow, it is easy to analyze, easy to understand. In practical situation, the speed is very high, we can't analyze what is happening. So, to see what is happening exactly, so we are taking the process is extremely slow. We treat the process is extremely slow. That process, that hypothetical process, that idealized process is called reversible process. So, this is the reason why we are using a reversible process in our analysis of thermodynamics. Now, let us discuss irreversible process. What is irreversible process? A process which cannot be reversed. A process which cannot be reversed is called irreversible process. Now, let us consider there is a small container, there is a cup of coffee, let us say there is a coffee there is a cup of coffee, it is at 100 degrees centigrade, let's say it is at 100 degrees centigrade, it's hot, it is 100 degrees centigrade. So let's say this is system. Let's consider the coffee in the cup, it is a system. This cup of coffee is a system. Outside there is surroundings. In the surroundings, let us say the temperature is 20 degrees centigrade. So cup of coffee is system, and outside in the surroundings the temperature is 20 degrees centigrade. So the system temperature is 100 degrees centigrade and surroundings temperature is 20 degrees centigrade. So since there is a temperature difference, due to temperature difference, we know heat flows from high temperature to low temperature. System temperature 100 degrees centigrade, in the surroundings there is 20 degrees centigrade. So high temperature to low temperature, that is system to surroundings, there is a heat transfer. So heat flows from system to surroundings. System is losing heat. Right now the system coffee is losing heat since it is at high temperature. And surroundings are at temperature, surroundings are gaining heat. System is losing heat, surroundings are gaining heat. After some time, the process will be over. Continuously, the system is losing heat. So system temperature decreases. System temperature decreases. Initially, the system temperature degrees centigrade. So finally, since there is heat loss, the final temperature of the system becomes 20 degrees centigrade. Once the system temperature is 20 and surrounding temperature is 20, so there will be no heat transfer. The heat transfer will stop. So after the process is over, whatever the heat lost by the system cannot be restored. That is the meaning of irreversible. After process is over, the process cannot be reversed. Surroundings not in a position to give heat to the system. Whatever the system is losing heat, it cannot be taken back. System cannot take the heat, whatever the heat lost, it cannot take back. And surroundings are not in a position to give the heat to the system. So once process is over, the process cannot be reversed. Since the process cannot be reversed, which cannot be reversed. So since the process cannot be reversed, this process is irreversible process. So what is irreversible process? An irreversible process is a process which cannot be reversed. And here system is getting affected and surroundings also getting affected permanently. System permanently affected and surroundings also permanently affected. So the system cannot be restored, surroundings also cannot be restored since they are not restoring their conditions, initial conditions. So this process is irreversible. So here system and surroundings permanently they affected. System and surroundings they permanently affected. So in irreversible process, system and surroundings they affect permanently. Permanently they affect. So this is about irreversible process. So system and surroundings they permanently affect. They change permanently. So this cannot be reversed. Process cannot be reversed. So this process is called irreversible process. Now let us see representation of irreversible process on PV diagram. So this is PV diagram and this is the representation of irreversible process, and it is a dotted line. It is a discontinuous line. This line, irreversible process line, is represented by a dotted line. It is a dotted line or discontinuous line. So irreversible process is represented by a dotted line or a discontinuous line. Now the question is, why it is represented like this, dotted line or discontinuous line? Since the process is very fast, between 1 to 2, during this process, the process is very fast in actual situations. The process is very fast. Whatever the actual processes are taking place in practice, in practical situations, so all the processes are irreversible. They cannot be reversed back. Since the process is very fast, between 1 to 2, as we can see from the PV diagram, between 1 to 2, the process is very fast. So that's why it cannot be represented by a continuous line. Continuous line we have seen. Continuous line stands for reversible process, we have seen. That is a solid line or continuous line, that is reversible process. But here, since the process is very fast, it cannot be a continuous line. So initially the point is 1 and finally the point is 2. Between 1 to 2, the process cannot be a continuous line. Since the process is very fast, we cannot see what is actually happening between 1 to 2. Since we cannot see actually what is happening between 1 to 2, simply we join 1 and 2 by means of dotted line. Simply 1 and 2 are joined by means of dotted lines. Now let us see conditions for irreversibility. Conditions for irreversibility. So we have seen what is reversible process and conditions for reversible process. But right now, conditions for irreversible process. Irreversibility means process is irreversible. So for irreversible process, what are the conditions? Exactly, it is opposite to reversible. For reversible process, what are the conditions which we have seen? For reversible process, the process has to be extremely slow. But here, for irreversible process, the process is extremely fast. In actual practice, whatever the processes are taking place, they are irreversible because they are very fast processes. They are very fast, which cannot be reversed back. So that's why these processes are irreversible processes. So here the condition is, it is extremely fast. The process is extremely fast. Process is extremely fast. But in irreversible, it is extremely fast. But in reversible case, it is extremely slow process. So here, irreversible process, the process is extremely fast. And here, there will be friction. Friction is present. Friction is present. In reversible, there is no friction, but here there is friction. Friction is present and process is extremely fast process. So these are the conditions for a process to be irreversible. It is irreversible, which cannot be reversed. Since the process is very fast, it cannot be reversed. And since there is friction also, it cannot be reversed. Some energy loss will be there. Due to friction, there will be some energy loss. So these conditions for a process to be irreversible. So for irreversible process, these are the conditions. Now let us discuss thermodynamic cycle. What is thermodynamic cycle? So this is the PV diagram. So thermodynamic cycle, it means series of processes. So 1 to 2 is a process, 2 to 3 is a process, 3 to 4 is a process, 4 to 2 is a process. These are series of processes. These are series of processes. So series of processes means, so one after another. Series of processes means one after another. So 1 to 2 is a process, 2 to 3 is a process, 3 to 4 is a process, and 4 to 1 is a process. So one after another. So these are series of processes. This is important. Series of processes. So when a system is undergoing series of processes, system is undergoing series of processes and restores its initial condition. Restores its initial condition. System is undergoing series of processes and restores its initial condition. Restores its initial condition. Restores its initial condition. So system is undergoing series of processes and restores its initial condition. So this is said to be a thermodynamic cycle. Series of processes. What is the meaning of series of processes? Just now we have seen one another 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So these are series of processes and restores initial conditions. Restores its initial condition. What is the meaning of this one? It restores, system restores its initial condition. So there are two important points here. So one is series of process and system restores its initial condition. Look at here. So system starts at point 1. As we can see from PV diagram, system starts initially at point 1. So initially this is point 1. So from point 1 it starts, and 2 to 2 is a process, and 2 to 3 is a process, and 3 to 4 is a process, and 4 to 1 is a process, where actually the system starts at point 1, where actually the system is completing the process at point 1. You look at here. So system starts at point 1 and again it is restoring to point 1. That is the meaning of restoring its initial condition. It starts at point 1 and again it is coming back to point 1. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So during 4 to 1 the final point is point 1. So initial point is point 1 and final point is also point 1. So this is a thermodynamic cycle. So series of processes and restores its initial condition. So this is a thermodynamic cycle. When system is undergoing different processes, series of processes, and again it restores its initial condition. So initial condition, it is means point, initial point is 1, final point is also 1. As we can see from the PV diagram, initial point is 1, final point is also 1. So that means it is a completing a thermodynamic cycle. System is completing a thermodynamic cycle. Now let us see what is a reversible cycle. Reversible cycle. Just now we have seen a cycle, thermodynamic cycle. So this is the representation of thermodynamic cycle. Just now we have seen. But right now, what is reversible cycle? Reversible cycle means in a given cycle, if all the processes are reversible, then the cycle is reversible cycle. All processes must be reversible in a given cycle. So this is a given cycle. In a given cycle, if all the processes are reversible, then it is a reversible cycle. And just now we have seen representation of reversible process on PV diagram. So how to represent a reversible process on PV diagram? It is a continuous line. It is a solid line, continuous line or solid line. So continuous line stands for a reversible process. So here each process must be a reversible process. Look at here. So 1 to 2 is a reversible process because it is a continuous line. So 2 to 3, it is a reversible process. 3 to 4 is a reversible process and 4 to 1 also a reversible process. Since each and every process in this given cycle are reversible, so that's why this cycle is reversible cycle. So all processes must be reversible. All processes all processes in a cycle must be reversible. Must be reversible processes. So, what is reversible cycle? All processes in a given cycle must be reversible. If all processes in a given cycle are reversible, then it is a reversible cycle. So, we can see from the diagram 1, 2 is a reversible process, 1, 2, 2 reversible process, 2, 2, 3 is a reversible process, 3, 2, 4 is a reversible process, 4, 2, 1 also reversible process. So, all are reversible processes. Since all are reversible processes in a given cycle, all are reversible processes, then it is a reversible cycle. So, this is a representation of reversible cycle. Now, let us see representation of irreversible cycle. Irreversible cycle. What is irreversible cycle? We know what is cycle. Series of processes and restores its initial point over that we have seen. It is a cycle, thermodynamic cycle. But what is irreversible cycle? In a given cycle, there is a given cycle here. If any one of the processes is irreversible, any one of the processes is irreversible, then the cycle is irreversible cycle. Look at here. It is a cycle because 1, 2, 2, 2, 2, 3, 3 to 4 and 4 to 1. Initial point is 1 and final point is 1. It is restoring its initial state. Starting point is 1 and final point is also 1. It is a cycle. It is a cycle. But here 3 to 4 in this given cycle, 3 to 4 process is irreversible process. 3 to 4 process is irreversible process. So, 3 to 4 is irreversible process. Even though rest of the processes are reversible, because 1 to 2 is a reversible process, 2 to 3 is a reversible process because continuous line stands for reversible process. So, 1 to 2 reversible process, 2 to 3 reversible process and 4 to 1 reversible process. 1 to 2, 2 to 3 and 4 to 1. These are reversible processes. These are reversible processes. So, 1 to 2, 2 to 3 and 4 to 1, these are reversible processes. Though these are reversible processes, 3 to 4 is not reversible. 3 to 4 is irreversible process. 3 to 4 process is irreversible process. So, that is the reason the cycle has become irreversible cycle. So, what is irreversible cycle? In a given cycle, if one of the processes irreversible, any one of the processes, any one of the processes is irreversible. So, if any one of the processes is irreversible, then a cycle becomes irreversible cycle. So even though 1 to 2, 2 to 3 and 4 to 1, they are reversible, but 3 to 4 is irreversible process. That's why a given cycle is irreversible cycle. So what is irreversible cycle? In a given cycle, if any one of the processes is irreversible, then it is a irreversible cycle, and this is the representation of irreversible cycle.